Yeah. Yeah. And I think happen again? Capture bus?
Yes, because they're going relocate these chairs to the back so unsuspecting people aren't.
Tilt it down a little bit. See the bottom floor? No, lift the left side over here.
Oh, I got you.
Should be able to switch the tablet. Are we on the rough space? Good morning, everyone. What's up, Matt? Hello.
Where do you want to sit? There? So you will maybe start this in the spring and finish it in the fall. Okay, so I have you for a whole more year. That's it. Okay. I'm gonna cry. But I know you're
Yeah, we figured that someone was gonna be the people are always standing. That's what I figured. Came in the pictures or something.
I am. Are you doing that? Nice to meet you.
Really?
A little bit.
Oh, look at it.
Yeah, I'm glad you could be here. She was excited for you.
Yeah, I learned it with next time somewhere else.
Are you graduating student or are you presenting
House
student?
leaves no arms, the house
Yes, yes.
I'm here to.
Oh, you can come back to
I'm
that.
here.
Oh.
Yes, I know.
It's fun.
I'm excited
No,
and
so
I'm
I'm
sad.
Yeah.
It's always such a fun to certain I really enjoy having her, and so they ask us
My brother needed.
to watch the writers and ask questions. It's just kind of for us. And it helps them. So you can, or
Yeah, I'm a civil.
You don't dress up for
yeah.
Yeah, throw a clean shirt.
Yeah, you like it.
I like it. Imagine how you feel.
Well, I didn't get it. And then, and I what you said, I didn't. And he was telling me, Daddy, tell my class. And I was back in the 70s. It was in the 70s.
I didn't know about my ask questions. I'm supposed to ask questions of Let's just do that. You got it. That's what I'm.
Following from here, you know where the town is? I'm he goes, oh, I supposed to take sure. First I end up, and then I show him how to say it. So he's down on everything.
Yeah, Angela Saints is the University of Texas. That's why we're team.
Yeah.
It's easy,
Now I'm gonna appear for the engineering section, right? That's a Thursday.
Yeah.
Graduation. Football. Yes. So early. So cold.
Had like 3 times.
Not that long.
Debbie was just born.
That's what she said. That's cool.
Well, he was already doing his 2 years.
Is he gonna stay in that? I was about to do that too, don't worry. Oh, yeah, well, I know she doesn't have a computer, but. I know, we're still. No, we're trying.
Morning, James, how are you doing? Good, how are you? All right, thanks.
Hey, how are you doing? I said, this is a dilemma now, the 21st century. Nobody has a pen. Are we really kidding? Nobody has a pen?
Yeah.
Hello? We have a problem.
Yeah.
We have a problem. No, I got a pen. I carry a pen
Yeah.
at all times.
Yeah.
It's making notes.
Yeah, right.
Our new generation. You find one?
A pencil.
Okay, I carry multiples in my purse. They're all times. These are things that one normally should do. Our world
Since you didn't have any of them.
has lost its.
Yeah. I'm not working, I carry a pencil.
That's funny. That is funny. No. I can't remember the time I was 6 years.
Yeah.
You can leave the back one open, but you won't leave the front one.
Wait couple minutes.
Love that.
It's just time.
Keeps here.
Are all the important people here?
You are. You're the most important people.
I thought you were talking about me specifically. Flattered.
You say that y'all are. I make it more clear?
All right, welcome to our capstone presentation. We have two mechanical teams. They have worked over their project. The first group is Driving 5, and they designed and tested prototype for a mu-slip curve generator for Goodyear. So without extending any further, I'll just give it to them.
All right, good afternoon, everybody. We are the Driving 5, and we wanted to thank everybody for being here today to watch our presentation. We also wanted to thank our mentor, Dr. Bob, for helping us out the whole year with our capstone project, and we also wanted to thank our client, Paul from Goodyear. So with that, here's our project. We were tasked from Goodyear to design a frame of a commercial tire testing trailer, and what that does is it tests commercial tire testing trailers, so like semi-truck tires, etc., on different type of surfaces, whether wet, dry, gravel, sand. And Goodyear actually has consumer tire testing trailers already. With that, they wanted a commercial tire testing trailer, and that is what we are here for. So once again, we are the Driving 5. And this is our team. So first we have me, my name is Demi Weaver. We've got Jesus Perez, Levi De Hoyos, Zachary Zapata, and Thomas Tilson. Since unfortunately today we could not bring our actual project up here, we wanted to provide you with some images. So the top one is just the side profile of our prototype, and you can see it's on some jack stands. We've got the front view of the prototype, the neck, and then the back side.
Okay, so just to kind of give you an outline of what we're going to be talking about today, we'll start off by defining the problem and, telling you what the scope of the presentation is, and then we'll go into, some of the planning stages that we did during, solving that problem, and talk you through some of the decisions that we made, before presenting the design that we ultimately produced last semester. And we'll also talk about the initial analysis that we did last semester on that design, and, talk about how we chose to build, or how we verified that that was safe to build, and what we, or excuse me, yeah, verified that that was safe to build. And then we'll go into the prototype manufacturing and talk about the manufacturing process before we go into testing that prototype. And we'll give you the results of the test and tell you what we did with those results before reaching our final conclusion.
So I'm gonna walk you guys through the scope of the project. So as Debbie was talking about earlier, our client is Goodyear, and we were tasked with designing a towable trailer capable of generating a U-slip curve for a commercial truck tire with the weight of 7,000 pounds per tire at a max speed of 60 miles per hour. So what is that? We can go to the next slide here. So what is a mu-slip curve and why is that important? So just to define these terms, mu is the friction coefficient of a tire. This is not ABS, this is the friction coefficient of the tread tire as it breaks, and this will change over time. The other factor that we're going to be measuring is slip. So slip can be defined as the relative motion between the tire that is braking and the speed of the vehicle that is pulling the tire. So as you can see here, the current trailers that Goodyear have generate these curves, and with this data, the reason this is important is they can redesign these tires to be safer for your vehicle, so you can brake faster, more efficiently, and the current goal, while we have these readily available for our cars, trucks, etc., they do not have these for commercial truck tires, i.e. 16-wheelers, semi trucks. So the importance of this is making safer tires for semi trucks. In order to complete this and do our project, we decided to break our goals into 2 semester goals. In semester 1, i.e. this spring, what we decided to do was verification of our design. So what verification is this is a comparison of our simulation models to analytical models. This is such as solving the problem by hand or using one-dimensional elements with simulation like Mastan. The main thing that we wanted to look at is max stress, safety factors, and elastic deformation. For semester 2, we wanted to go ahead and validate our design. So validation, this is taking these simulations and comparing them to real-life experiments. Usually this is accomplished by prototype testing. So the way we did this, we will discuss later on, but essentially it's a scaled-down test that we can perform in real life, compare it with a simulation, and then we know that our simulation results are valid.
So when thinking about what it's going to take to bring this trailer to fruition, we broke our project into 3 distinct phases: the structural system, the control system, and the electrical system. This project, this capstone, focused purely on the structural system as the items listed there. We'll go over these now. The frame has to be able to hold 7,000 pounds tire load and or 14,000 pound axle load. That's the client requirement. We want it to be bumper pulled. That'll allow it to fit in easier with the rest of the tire testing fleet. It's easier to mount and dismount from the tow vehicle just for operator's sake. And the tires cannot be in line with the tow vehicle. That's a testing consideration, especially when it comes to wet traction testing. We'll get into that a bit more later. The loading system. This is just what we call how the weights are going to sit in the trailer and where. Of course, it needs to hold up to 14,000 pounds safely and securely. Importantly, it has to hold 7,000 pounds on the testing tire. So you can't just put the weights anywhere. It has to be, you have to put a little bit of thought into it. Of course, the low center of gravity, that's just an important safety principle in the first place. the axle and suspension. Before we could get around designing the frame, we needed to know what kind of axle we're gonna use, especially when it comes to the size of the axle housing. After perusing the internet for commercially available axles and suspensions, we came across this particular one. It's axle suspension combo, great, 20,000 pound capacity, great, supports dually tires. Now, that's not a frame consideration, but we like to include that as a damage mitigation feature. We imagine putting a smaller diameter tire on the outside of the testing tire. So in case of maybe a blowout, the trailer's gonna drop on that secondary tire, not damaging the track, not damaging the frame. So that's that.
So then, after all of the scope, we went on to planning and design. After knowing the project and background, we also got to go to the Goodyear Proving Grounds with Paul, and he showed us around the consumer tire frame. So we got to look at that and how they were loaded, just to get a little background. And with that information, we came up with 3 different design approaches. So the first one you can see, we were gonna scale an existing tire trailer that Goodyear already has, the consumer ones. And with that, it would be a pro to validate our results with existing trailers, but a con is that the loading system may not work with the amount of load we needed to put on our design. Secondly, we could creatively design a whole new frame. So a pro with that is creative design freedom, but one thing that could go wrong is reliability. It might not be proven, it might not be safe. We wouldn't know because it hasn't been done before, and it's like from scratch. And then the third is to modify an existing trailer that is able to hold 14,000 pounds. So this is just like looking on the internet and finding any trailer that would be able to withstand that load, and we could modify it that way. With that, it's easy to acquire, we just buy it. But some cons is it might not be able to modify the way we have to via standards and etc. So we took those 3 options into consideration, and we considered a few things to score them in this design matrix. So some things we looked at is the initial investment, and the higher the number, the better the score. So the first one, initial investment, we rated manufacturability. How easy would it be for us as a team to manufacture on campus in our lab? The load distribution. So like Tom said earlier, it has to have 14,000 pounds and a certain amount of weight, 7,000 pounds on the certain tire. Would the design be able to do that? Design complexity. Once again, could us as capstone students design that complexity of that design? Adaptability, if something were to happen, would we be able to adapt to it? And then the time investment, would we be able to finish it within the manufacturing semester, which is just the fall 2022. With that, we've got our scores right over here, and as you can see, option 3, the modifying a store-bought trailer was ruled out. So now we have these 2 design options that we more closely considered. So first, scaling an existing tire testing trailer that Goodyear already has for consumer tires. We looked at the proven design, which is an offset trailer, so it's not in line, the actual tire testing trailer. We also looked at the alternate design. We came up with one with a 3 tire design. It's also here, just to provide more information on that 3rd tire. With that, we went on to standards.
So we had to find some standards that applied to how we were going to build this trailer and what kind of testing it might be subjected to. And we came across ASTM F408-21, which describes the testing purposes of this trailer exactly. Wet traction, straight ahead braking using a tow trailer. So, first component of that is the trailer shall be equipped with a tow hitch and 1 or 2 twist wheels shall be instrumented as described. So 1 or 2 tires, easy. Next, we relate our hitch height to other geometries of the trailer. Basically, the hitch height, if it's X, has to be less than our loaded tire radius and less than 10 times our axle centerline to ball hitch length, which we designed the trailer around it, made it works. Next, we'll talk about the trailer tire tracks. The tire tracks of the trailer have to run separately from the tow vehicle tire tracks, especially during wet testing. The sitting water on the surface, if you can imagine, if the vehicle runs over it, it's going to influence the water on the surface. and influence the testing tire in the rear. So those have to be offset by some amount. Fortunately for us, at Goodyear, they already have offset ball hitches, so we didn't have to account for that in our frame. Next, if you've heard of the 60-40 rule when it comes to determining where an axle sits along a trailer, that's what we tried to do here. Couldn't quite get 60-40, it was more like 65-35, just to meet those standards mentioned previously. Now the balance weight forward and back of the tire, that relates to the actual load that we're putting in our bays to load the trailer up for weight. The important part is that they're both equal in front and behind the tire. And it's gonna maintain pressure on the ball hitch just by the weight of the neck assembly. That's just an important trailer feature anyways. This calculation proves that our ball hitch has pressure on it so long as the loads are equal in front of and behind the axle. In our loading method, after a visit to Goodyear, we looked at their inventory of weights, and we settled on this particular one pictured. It's a 2,000-pound weight. It's got these rails underneath that are gonna fit in our trailer well. Once those are on, it's gonna require some fine tuning with smaller weights just to get the trailer to exact load, and especially with the testing tire to the exact 7,000 pounds required. But that's done before a test anyways.
So these were the design iterations that we went through last semester. As you can see for number one, we had gone with the 3-tire design, which was in line. But after discussion with Goodyear engineers, we decided that this may not be the best idea, especially for Goodyear, after discovery of both the offset standard as well as the offset ball hitches at Goodyear. So that moves us into 2 and 3. Number 2 just genuinely sucked, I'm gonna be honest. So we didn't really follow any principles, we just wanted to get a general idea of what this frame would look like. Number 3, after better consideration on how we should design the frame, we took into account the clearance for the actual axle and suspension, and as well as what the ideal spacing will be for the weights at Goodyear. And then number 4 is our final design. So our final design is a 2-tire design. It has a reinforced midsection for the axle and suspension combo, just to make sure that the bending moment isn't too high. We finalized the clearance for the axle and suspension. We used the appropriate beams for the loading materials at Goodyear. And then finally, the hitch offset reached the standards as well as the range that Goodyear's offset ball hitch has.
Okay, so the initial analysis, this refers to the analysis that we did on the design that Zach just explained. So first we began by using MASTAN, which utilizes single dimension elements. So we did this so that we could use it in conjunction with FEA analysis, finite element, because this one provides quicker results and is pretty accurate too. So initially we did this analysis. This is the full scale. So we found that with the full load, it has a displacement of 0.36 inches with steel and 0.37 for the stainless steel in the back. This is the same analysis, but we did it on a half-scale model for the prototype that we're going to be designing or that we designed and we're going to be building. So for steel, it had a displacement of 0.26 inches and 0.27 for stainless steel. So this analysis right here is the analysis we did with finite element. We use Nastran for this. So this is showing the element thickness. If you can see, there are 2 elements per thinnest part of the trailer, and that's important for our accuracy of the results. And here we have the boundary conditions at which we constrained it. So axle connection, that's over here in the front. You can see that it's where it's red is where it's constrained, and we have a symmetry constraint too. So if you notice, this thing is cut in half. The reason we did that is so that we could save time when doing these analysis and computational power. And we also have the connection of the axle, which is right here in the middle. Okay, so as Jesus said, the purpose of the Mastan, simulation was to verify it against the FEA simulation to make sure that we were getting similar results. And, we did have we ran multiple simulations on the half-scale model, and varied in element size, which is there on the bottom of the convergence plot, and found that the displacement was beginning to converge and was beginning to converge at around 0.21 inches, which was within a margin of error of the Mastan simulation. And there, we found that the max stress, which can be better seen in this upper right image, was about 111 KSI. So with that knowledge, we went on to analyze a full-scale model, which is just the prototype doubled in every dimension, and found these results, and took into consideration the margins of error that were mentioned previously, and found that they had a safety factor of 1.25.
Right, so when we first started building our prototype, first thing we had to do was figure out what kind of weights we're gonna be putting in the bays.
Sorry, this is my slide. So for prototyping, we decided to build a half-scale model. We pretty much did this by halving all of the dimensions, as we'll see in a second. But this is just a preview of how they relate to each other. So for prototype testing, we had a couple of goals that we needed to meet. So first of all, we needed to load this with 1,000 pounds to induce a significant stress that can be measured. If you'll notice that this is not a half scale of the full scale model. So the reason for this is just practical limitations. So we had to get these weights from the gym, so we were only able to get about 1,000 pounds instead of the 7,000 pounds that would be necessary for a half scale model. Also, the axle and suspension will not be included, but we did replicate these points accurately. So we did this by modifying some jack stands and connected them to the trailer. The same thing for the front connection of the ball pitch. And then finally, the things that we're going to be measuring were deflection, stress, and strain. And we were going to compare these against the FEA results.
Okay, so now is the point to where we needed to figure out the material for our project. So our team decided on AISI 1018 carbon steel tubing, which is rated for 52 KSI max yield strength. And if you look at this little diagram up here, it'll show you we use tubing with a certain thickness, which our full-size scale would be a 1/4 inch, and our prototype, which we did build, was an 1/8 inch. And then we used 4x4, 6x4s, and 2x2s and 2x3s. So in our prototype, you can see our 2x2 by 1/8 and our 3x2 by 1/8. And this is just the material selection that we went with. Then we went and created a CAD drawing for our prototype. So this made it easier when manufacturing. We got to label the members. So with respect to the measurements and the size, lengths, etc. of each beam, we were able to create an Excel sheet to simply label everything so we could know the lengths and how much we needed for later on when we needed to budget. So that is just what this Excel sheet is. So from here through the neck, that's the 2x2s, and then at the bottom, we've got G's, which are 2x3s. So using that method before, we were able to break down how much of each steel beam we needed, steel tubing, and we created a cost breakdown. So here it is for our prototype. We did not include labor costs, but we did include manufacturing costs. So we've got the welding wire and the welding materials. We also have the jack stands, which simulate our axle, and the tubing. We also did a 10% contingency just in case, so our client would be able to give us money up front and we would not have to ask for it at the end. We also went ahead and added extra tubing just in case we were to mess up during manufacturing, because as a team, we did manufacture this trailer ourselves. With that, the prototype came out to $1,450. and we can compare that to the full-size trailer. If this were to be built by Goodyear, we also included the manufacturing cost minus labor, the tubing, and a 10% contingency, giving us a total cost of $12,100.
Okay, so when manufacturing, we began, like Demi said, we divided the whole trailer into sections and labeled them according to letters. So we were able to print out these pieces, or these sheets that told us how big and the dimensions of each member that needed to be cut, and we followed this when cutting the beams. After we got everything cut, we started welding, and if you see here, we began by welding this part, and then we connected it with the axle housing, and then at the end with the neck. So here's some notes. This is one of the harder, more difficult situations we ran into. If you look at the neck, there's an angle going down and there's an angle right here, but it's also going inward. So that means 4 angles, considering 2 members. So we had a really hard time welding that, or cutting that and putting it together, but we were able to figure it out and get through that.
All right, now for our testing procedure. We had to figure out what kind of weights we're gonna load the thing with. We settled on gym plates just because of the accessibility. But you'll notice they're these polygons and they don't sit very neatly into our weight bays on our trailer. So we whipped up these baskets. These baskets hold the weight snugly and securely, and they apply a square load on our supporting members of our frame. Here's just some pictures of cutting them out, welding them up, and how they sit in the trailer. There'd be one in every corner.
Okay, so this is the testing setup. As you can see, we put it with the jack stands. When testing, we wanted to compare our experimental results with our analysis that we did earlier. So to do this, we use strain gauges and a dial indicator for displacement. So here's also the test, how we did it. We have 500 pounds on each side. We kept it evenly, and that picture just shows how we kept it leveled so that the forces could be uniform. So here we're talking about the strain gauge locations. Each one of those arrows indicates where we placed the strain gauge. The reason we placed them at those spots was because those members would be having uniform strain. So that would help us get an accurate reading from the FEA analysis. Here's just the procedure that we used to connect these. We just sanded them. We sanded the trailer. We cleaned the surface. We placed the strain gauge on a piece of tape. We glued it. And we just secured it there, and we connected it all to the reading box. So as of safety, I think Zach mentioned this, we modified these jack stands. That's how it initially came, and we ended up welding a plate on here, and this little rail so that it wouldn't be tipping. And that's how it is. Okay, so with the test result, or after having tested and gathering results, we went into, these are our results for the test. The max displacement was 0.379, and we had strain, micro strain at the 7 different spots of that magnitude. And so after garnering those results, we wanted to compare them against the simulation to validate the simulation. And we induced a significant stress on the prototype in order to to have a measurable strain. And and the plan was to compare that strain against the prototype simulation. The simulation was created by making sure that the contacts were all bonded, meaning each beam had a bonded contact between itself and another beam, which simulates a weld. And the load negative, or 500 pounds was placed in the negative y-axis in both the front and back bays, and gravity was taken into consideration. Also, the constraints are there, as you can see in this table. We ultimately settled after much deliberation on these boundary conditions, which, if you recall, are vastly different than the ones that we used on the analysis last semester. And it's because they most closely represent, we believe that they most closely represent reality. And the green box there in the ball hitch, on the ball hitch, represents its ability to move in this manner. This box is fixed on all axes, excuse me, and separation is allowed between the trailer frame and that box, and sliding is not allowed. And that's important because it better represents reality. And then the average mesh size was 0.125 of the simulation, and there was parabolic elements were used, and this was our element and node count. And the materials that we used were type 304 stainless steel and AC 1018 cold drawn steel, and this is their modulus and yield strength. Yields, yes, continue. So the prototype simulation had a max stress of 9.72 KSI and a displacement of 0.08 inches. And as you can see, we ran a number of different simulations on this prototype, and the elements varied in size, and it is indeed converging to these values.
So this is our strain validation. So if you can look at this table, you can see we looked at each specific location. We looked at our experimental strain versus our simulation strain. And something to note is some members have really, really close results and others not so much. So to specifically point out, our members 5, 6, and 7, specifically this member here, did not really accurately represent reality. We think that there was either errors in the simulation or we just had manufacturing errors when welding these specific pieces. Nonetheless, other areas like this one here, and then this other opposite strain, and then our top strain were really accurate. Accounting for all of this, we had an average percent error of about 20%.
So the displacement, which we originally measured to be 0.379 in the experiment, as you can see there on the radio gauge, had an average percent error, or had a percent error of about 88%, with the simulation producing a 0.0432 inch displacement. However, we did have to take into account a source of error with the jack stands. The jack stands under the load compressed, and the point of contact at the front, because of the type of jack stand that it was, didn't have as much, or didn't have any movement. So we used the rule of similar triangles to determine that the jack stand, the compression at the jack stands was exaggerated at the rear of the trailer and produced a 0.18 inch error. And when adjusted, the percent error was 40%. So taking the 40% error in the displacement and the 20% error in the strain into account, we ran the full-scale simulation and found that the max stress was 86 KSI and the displacement was 0.3 inches. However, as we said earlier, we originally planned on the material to be cold drawn steel and for the dimensions of the tubes to be a 1/4 inch thick. And when both of those things are considered, the material actually yields. And we can be sure of this because not only is because the simulation is validated and because the simulation is seen here to be past its yield stress, which is why it's not converging while the displacement, or unlike the previous simulation.
So with that, we take this into improvements and recommendations. So after taking those results into account, we decided to redesign our trailer for a final time. And with that, we were able to get, so firstly, we changed the wall thickness. We increased it to about 3/8 inch. This is also a readily available sizing for these tubes, which we always wanted to take into account. We also added additional axle support. As you can see, we added cross members here, as well as made this thicker and doubled it. With this, we reran our simulation with the similar boundary conditions and found our max stress to be 22 KSI within the linear elastic range, therefore not yielding. With that, we also found a displacement of 0.185 and a safety factor of 1.4. But taking into account the safety factor, I would like to share with you guys a screenshot of our results here. So this is the bottom part of our axle connection where our frame sits on those jack stands. If you'll notice right here, we have a maximum stress, right here. But if you'll notice, it's only in this corner. And if we take into account this color graph here, all of the rest of our profile is well half. So we likely have a much higher safety factor. Taking into account these results, we've come up with a couple of solutions. Yes, that's okay, go ahead. So first of all, crucial frame members should have bolted connections. This is taken into account the effect called haze. So heat affected zone from welding stainless steel. These type of effects will sort of make it a non-linear behaving material. And considering we have a sort of higher range of safety factor, we just want to make sure that this does not fail. Another thing is redesign of the net connection, our double angled part. This took us about a day to manufacture and then connect, so redesigning this to be more efficient to build as well as more reliable would be very, very crucial. Another thing is we should retest the full-size trailer under similar conditions if possible. This would be suggested to do at the Goodyear site using the weights that they have available. And with that, we just want to again check with the simulation to make sure that this frame will not fail. Another thing that we would like is to consider changing the axle connection beams to rivet connections. So the axle suspension combo that we had chose had 2 loading options. First, the one that we had chose was a simple weld bracket to the frame. This is a flat piece of steel connected to another flat piece of steel that is just simply welded in a box. The other option is most commonly seen in these types of axles that they actually put on the 18-wheelers. They use a long, flat steel beam, and with those connections, they just rivet into the sides with additional flat planes. This is just considered a little bit safer, this will take into account nonlinear deformations, the issues of the high stress at the weld connections, and the only other stress that may be present is just corrosion. But with that, thank you.
y'all do your own welding?
Yes.
Did you test your welds? Because you talk about how it changes the metals and stuff. No, I'm just curious, because you did your own welding, so that's really neat. So, did y'all look at that aspect of it?
No, we didn't consider the,
And then the other aspect, do you have any idea how many hours y'all spent? Because I'm curious about your labor costs. Like for you guys, how many hours you spent, kind of get a general idea, because labor costs are double usually what your materials are at least. And so, y'all, y'all kind of keep track of that at all? I'm kind of curious.
We didn't really keep track of it. I'd say that, it could probably be estimated to be somewhere between 40 to 60 hours.
And on the manufacturing piece, so you add all that. Very good. Good design.
So, go ahead.
So, so slide number 50, can please, so how do you end up which element size is the best? Because it's increasing, so maximum is increasing as you increase the element size. So how did you end up which element size is the best so we can choose this element size and then continue your simulation with that specific element size?
So, in order to determine the best element size, you kind of use a rule of thumb and say like the thinnest part of the material should have two elements, a 2-element thickness in it, and the 0.125 element size produced the 2-element thickness. And the reason for that is because stress is a localized phenomenon, and the larger the element size, it just begins to do the average stress in that area, and the smaller that the elements become, the more accurate that average becomes.
Another thing is just mesh convergence practices. So in CAE, the class that we take here, we usually commonly perform simulations and take a look at mesh element sizes as well as their types. So specifically for this type of test, we use parabolic elements. So with these type of elements, they use double the amount of nodes, so they quickly are converged to an accurate value. So like in this chart, for example, here, as you'll see, we have our element size of each one. Usually we'll have a similar behavior like this of an almost exponential growth. And towards these two areas right here, we'll see that there comes a point where changing the element size doesn't change the results that much. So that's what we call mesh convergence. This is pretty much saying that even if you get the finest element down to like the atomic level, you're gonna get the same results. So it's better not to waste that time with additional computational power when you can be confident these results now.
Why did you decide to use those kind of elements? Why didn't you use like plate elements or something that was more efficient?
So specifically,
You're just using solid elements for everything, right?
So,
So why didn't you decide to use plate elements for the size of the thing? You could have used way fewer nodes.
so another option we could have had, like you said, would be shell elements. So this is pretty much taking these elements from 3D to 2D, and that would have been a lot easier. Honestly, the reason that we went with that was because it took a lot of man hours to really draw this CAD drawing in 3D model. So in order to save time and meet deadlines, we currently wanted to just simulate using 3D solid elements. And we had a lot of practice being confident in those types of simulations.
And actually, we did try to use 2D elements, shell elements, and we were running into problems at the points of connection. Because two shell elements cannot be attached by their edges, but you would have, in order to create this boxed structure, you would have to attach elements in that manner.
Yeah, you have the luxury of huge amounts of memory and computing power, I just would like to point out.
Yes, yes.
You brute force this stuff. Back in the day, it was different.
Yeah.
What kind of welds did y'all
For the welds, we just went with the MIG welder.
What type of weld was it? Was it like a fillet weld? Was it a full
It was a fillet weld.
penetration weld?
Yeah, it was a fillet weld. We didn't do full penetration. They're just sat on top.
And then in the design of your frame and all, did you consider some sort of fatigue loading? Since this is gonna be like a trailer that's bouncing around and running around the track?
I was gonna ask the same question in relation to your factor of safety. How did you calculate the factor of safety, and did you include fatigue in that? So,
Yeah, that's just the immediate factor of safety. We did not do a fatigue analysis. We felt that it, we had a reason for not doing it, but I don't remember why.
How do you make a recommendation about it? What would your recommendation be?
For the fatigue,
I mean, are you concerned about it for your design? Or are you not
Specifically,
concerned, or what is concerning?
due to the material of this being stainless steel, when we were taking our materials class with Dr. Hawk, like I had mentioned earlier, haze is something of concern. So using specifically welds on this, it may cause it to fatigue or have more deformations faster than what we can normally see, especially with so many members being welded and under such large loads. I definitely do see fatigue being an issue, but at our current point in time, we just want to be able to put out a design that Goodyear can use and make road safer as fast as possible.
I wonder if you pointed out at one point that your factor of safety was based on a very small stress concentration at one point, but in a fatigue sense, that might be the epicenter of your actual root of your failure, so.
And I have a question on that too, because you switched from carbon to stainless. You talked about the connection factors and stuff like that, but there's a big cost difference. There's a difference in how you have to make your connections and all that. And again, back on the fatigue and the wear and tear and all of that. So what was your reasoning again for going from carbon to stainless? And again, with connections and fatigue and that kind of stuff, all those relate into that.
So specifically for the reason for the material switch, we apologize for not mentioning this earlier, but
That's just curious.
at Goodyear, whenever they're performing these tests, they have two types. They have dry testing and wet testing. So dry testing is just putting it on a dry road, driving it, braking it, see how it does. But wet testing is they first pour water over the road to simulate rain environments and drive. And because this is an aggregate, whenever it is driving, it's kicking up these rocks as well as water. So what they've seen in the past with their regular steel designs and just simply coating them, they quickly get degraded, perform rust, even polishing, etc. It just really quickly wears down.
Sure, and so that's really a preference they've learned over time as well.
Yeah, so to put
Okay,
that simply,
which
the
makes sense.
customer wanted us to try out 304 steel, or stainless steel, excuse me, to mitigate weathering, but we did, when we were running the simulations, we actually did run them both with, the 1018 and the stainless steel, and, like making this change at the end, does not affect the results greatly. And then, Dr. Kitch, what was your question before? I felt like I wanted to get back to it.
I was just asking about the factor of safety calculation, but you did not do a fatigue analysis.
No, we did not.
That's fine. How would that change your approach? I mean, just a general questions, and if you were to include fatigue in the analysis, what would that do to your approach or your analysis, or
I think we would have a better understanding of the, the usable life of the trailer, right? And it might, assuming that we find the trailer designed this way is only gonna be good for 6 months, then we would definitely want to change it, you know? Hopefully it's closer to a 10-year lifespan.
Likely for this material, since these are such high loads and high stress, we would want to find another way to decrease the stress, such as like adding more members, making thicker walls if possible, if they're commercially available. That would probably be the best solution to that problem.
I wondered if there's a standard for trailer fatigue loading somewhere in the standards. I don't know, it's just, because trailers are moving and doing things all the time, and I use trailers a lot and racing on it, so yeah, and they do fatigue break off.
That's something we'll have to look into.
So one of the advantages we have is this is a precision tester.
Yeah, y'all are
So,
like us.
so we don't have a lot of potholes, we don't have a lot of bouncing going on.
Yeah,
Um,
which we do all the time out there.
Yes, so it's not quite a road trailer, so.
Yeah,
I would be interested in the fatigue loading, but it's probably not gonna be a high frequency.
and your semis
Fatigue.
don't run over ranch roads, they're running over mostly highways and things
Yeah,
like that.
well, particularly for this test. And we're not testing the semis, we're testing the tires.
The tires, I mean, your semis that are running the tires. are
Yeah,
running
so we
over,
want
yeah.
that, we want as little bounce in that as possible, so that we get good contact throughout the test. We've actually had to do repaving and precision paving in order to get that smooth surface to prevent inducing any kind of sinusoidal wave into the test, so.
Any further questions?
What kind of connections do the existing trailers use? You said you were recommending going away from welds because of the thermal damage, or whatever that's called. Do the existing trailers, are they welded out there, or are they bolted?
They're welded. Yes, the existing trailers will be here. But these are for usually car tires, so.
Oh, yeah, smaller loads, right?
Much smaller.
Don't they have some that are for really large loads? One or two, are they different?
This is.
Goodyear specifically?
We do actually have
You're talking like really big ones.
earth mover tire loads, yeah, so like, 60,000 pound kind of
Is that one
trailers.
welded or is that one bolted?
Welded. But it's a lot fewer elements, it's more of a flat trailer with the frame underneath. We don't do slip testing. It's predominantly load testing.
That is something that we forgot to note, which is that, like, this trailer is not something that's commercially available. It's, and there's only,
People don't make slip trailers? I thought I could get them off Amazon.
you actually can buy one offline, but it's not for a commercial tire. And
It is actually not only is it a US label grade test, it's also a European label grade test. So there are a couple of commercial trailers available, but as Levi said, not in the category we're looking at.
all right, thank you, everybody.
Thank you.
So we have a second group of mechanical engineering team presentation, and we'll start at 1:15.
If you guys are. Like the birds. Like the birds? Yeah, they did a good job. I made a note, one of the things I like. Slide that I can't test it. See, look, hear me out.
Oh,
This third grade?
it came down to like a time, like once they have the prototype, and there's so much they can do, so.
Right. No, yeah, I knew it was constrained. I also recognized that it was probably gonna yield. So I was not surprised when they put that up, that it had in fact, because, and I made the comment at one point, when you go down by a factor of 2 in both directions, you're actually reducing by a factor of 4.
Wait, you with me today? And she's like,
So
we'll just skip and you'll see.
Yep.
But they were running iteration like even like last week. I mean this weekend they were also running iteration.
That's part of the challenge, the deadline is there, so. But all in all, I think they did a really good job. I appreciate working on the project with you, I look forward to getting some more, as I come up with ideas.
Yeah, in the spring I'm gonna start looking out for.
They should have been fast. I mean, we were trying.
Keep an eye out, I've got one right now for civil engineering.
Oh, okay.
We'll see where it goes.
That's what you're about.
No, it's okay. I got classes. Okay, you're good. Cool.
You gotta make sure your cabinets are
It's
running.
an hour, yeah, it's an hour and 30-minute drive. No, if you look at 7 AM, I'm not used.
12 years.
Are you watching the next one?
Yeah, we got it. We just left the Lexus. I gotta turn those back that I stole from that guy.
I don't know.
I just decided, yesterday I was on my phone, I thought, I'm just not gonna make a rush. Yes, sir.
Thank you.
So here. I gotta go get it. Oh, well, thank you, I love that, cause it's my husband. And so this year is gonna be.
This is my dad.
Great.
Finally changed, huh?
That's not taken.
That's okay, that's good. I'm gonna go. I need to go get on a hard surface, so I can write these down. I need to go get on a hard surface. Careful your pad, thank you.
Why the book? Why the book?
No, they. Oh, I got it, there's somebody's question, so now.
Brian. I'm ready.
My head outside.
I told my parents to watch last year. I told them to make sure I go out.
He just said, no. He said, we got few of them, but you gotta do to get it done. So I was like, I don't have a afford. See what time do they open? Get out here. They've been open just one
There's one thing I'm wearing tomorrow.
Wait, what time is yours? 2:30. 2:30? Oh, I thought yours was because I gotta work on that mechanism project. But it's on Facebook, right? YouTube. What's the link? Because I can stream it. Look up the visuals.
Y'all did good.
On YouTube.
We're done. We're over.
Yeah.
We were just out there. Oh.
Or Dad? Oh, that's me.
That's me, Derek.
Yeah, I mean, it's
like
hard
Jones.
desert, and, but Tucson itself, you know, there's a lot of irrigation and.
You wanna put us in lighting here?
I think it's still on.
That's what I was thinking.
I mean, it's significantly bigger than. A lot more expensive. I wouldn't say it's less. It's got a much bigger city, a couple of major interstates. There's a lot of stuff going on. That side of Arizona, there's a lot of stuff.
I can't wait to look at it.
Think about it.
Yeah, well, you were enthusiastic.
I just found the
He's always been enthusiastic.
Slow, you wanna talk when you're presenting, you have to talk as you think you're going slow. And that's probably, I mean, that's a good rule of thumb for the speed for your audience. If you think.
Are you
you're
done
going
again?
slow,
Doing
all right.
I
I don't like the key right now.
At the very beginning, you started off like.
He's giving it.
I was like, whoa. When it came back around to you, it was definitely.
I got on your page.
You're in the middle.
If you.
That's a little less than that, but, you know.
One of the best classes.
So how'd you got your simulations done for the?
Videotaped it and.
As best as I could.
Yeah, and what's the thinner tube look like?
It was using that material, those tubes that you handed me the other day, it was using those ones.
It's a good.
What kind of altitude did you get off the G's?
1,050.
And that's actually a really great.
That was after taking into consideration the bulkhead of the payload and everything, all the support that goes into that.
Because there's a lot.
I dropped it down quite a bit. But we're getting it down.
I've never done it, but I highly recommend.
Well, I'll look at those and then I'll look at some of the other motors and try to get an idea what motors on it works.
I feel like it just makes you.
Right now, this simulation uses the highest G that I was able to find.
Like, I don't know, I'm thinking, I hope I.
I think that's the low, that's a high power.
You know.
Yeah, it's got too many grams.
When I was in.
Yeah, I'm pretty sure it is. That's okay, well, the G80 or the G60.
Presenting a lab result.
It might be not that much less
Everybody.
altitude because the slower,
And then when I got
the
to here.
slower burn is gonna give you less stress.
We had a couple of presentations.
I got my schedule now, I know we're gonna be leaving
I was in
on
college, I did not like.
13 to come back.
I still don't like speaking to if I don't have a caption.
I don't know if you guys are ready to do a test before this, yeah, at least get your ground tax.
Even if you're.
So I was thinking maybe tomorrow at the latest, we can get stuff from
So what do you need to order?
It's a great learning experience. Teach you to do it well. You get to practice, and everybody's in the same boat, so it's.
Glues and all that stuff. You got all the body tubes, you got the nose cones.
The nose cones, I switched it up from the previous, from one that I found that fits the Estes.
Right.
It's more
Because the
difficult.
nose cone that you have is an Apogee.
Doing it
No,
online-
Aerotech.
doing it well online
This one is
is
Estes,
tough.
so it should fit on this
Doing it well
thing.
in person where everything.
This nose cone we have.
The nose cone that we have, I think it's just a little bit smaller.
No, I'm sorry, the nose cone.
People aren't distracted by what else. is
The
going
nose
on.
cones that are in the lab, I think when they.
Oh, from that one? I can, if it's.
What I'm saying is it's easier to.
No, you get a structure as I understand.
Well, that nose cone is only like
Did you
$5.
put the,
They're different.
GPS in there?
You have to get.
Put it up in the nose cone?
No, this was sitting in the payload cover. Since it's so small, I decided to move it up.
So you have the altimeter and the GPS in the eBay?
The eBay has just the two altimeters and their batteries.
Okay, so you sort of have like two eBays essentially.
Yeah.
One for the, one for the.
Yeah, one for the GT.
In schools, writing it all out. Address, how you stand. If you're Italian, you have to sit on your hands.
Trying to remember what, oh, so so you have two couplers and your separation cord. So from the bottom up, you got the eBay, you got the second coupler.
The second coupler.
The second coupler is actually your full scales
Send
where
me the final presentation if you will.
the payload extractor mechanism is going to go right.
Alright.
So your injection charges are all both sides of the eBay, right?
Yeah.
And is the second one separating at the, is the upper section separating at the eBay or the second?
Second section separating up at the payload.
Okay, all right.
Yeah, so there's no need for
Last day is
a
the 30th.
Yeah, so your top payload is basically empty and this one replaced it with mass or whatever. right?
For a while.
When you're able to get the center of gravity in the right place, did you have to have mass to do that with?
Because no, if you just kind of look at it like that, it's nothing to
Too far
stability.
forward, or too far back? What's
Just to be somewhere,
Type of-
at least 6 and more.
So
You can,
the center of gravity is a
you
little
can
too
say
far
something like
forward.
that, something.
Well, we should
But I feel like I
give
can use my,
or something.
exactly.
If you really want to say, I mean, I think that's something I really want to say.
Center of, okay. I can mess with it.
Oh, yeah.
Well, we can just put weight something. I think the easiest way to do it. Like figure out what the minimum mass you need to add down to the booster section. You want-
Like, come on.
Must be nice to
Not a sliding note.
And I'm not gonna say no for me. Put him on the spot.
You also did it already?
The what?
You also did it
GPS really isn't that heavy.
Yeah, yeah.
No, it's very, very light.
Where is it?
Those are actually pretty heavy.
Oh, hot plate.
Try to think what's breaking the mass.
Yeah.
Really?
Because I was in the bathroom, so it's used to that up there. But it's
You got the
more hot.
payload up front. I'm thinking this one,
Yeah, this is dry.
mass would be
Dry too?
But it has more
lower than.
places to go.
Yeah.
So
Yeah, so the prototype center of mass is higher up.
So, and I have to say, I just told her this, I forgot my, my question.
It's a little bit lower,
Are
because
you
on the front,
planning
I don't have the
license?
payload separated. It's there, but I have it off.
If you-
And I do have it
Trust,
on the
take your
open
fundamental
process.
exam, get your license, I'm a licensed engineer.
Yeah, so what you wanna put in that, so in the same bay as, either in the nose code,
And they don't, we don't force that, we don't teach that.
the bay that's gonna,
Yeah, we,
the payload.
that allows you lots of other options later.
You need to put enough mass to
You
get the
cannot-
center of
If you work
mass
for a
of,
corporation,
prototype
like
is
Johnson
same
Johnson,
as
like I
your
work for
full
Alcoa
scale.
or whatever.
Okay,
Yeah.
You're
so it'd be, the lowest weight would be
Technically,
the
you're
nose
licensed,
code.
but you cannot go out and consult.
So I think we ought to figure out
Like
how
I've
to
done
do
for
that.
20 years, you can't go out and consult. Quite all right, they're good, aren't they?
Forcibility.
Without your license.
Like way more.
And so, yeah, your degree is great, but your
Are you
license
using
is
canards
like
or
a
not
doctor
using,
has a
using the fork
license.
fence or not?
And lawyer has a
For this one,
license.
yeah, we're gonna
Pass the
be,
exam.
and I have an
Take
idea
your
to how we can get it all
fundamental
perfectly
exam,
straight.
practice exam, and then 40 years, and 20 years from now, when you decide you don't want to work for a company. and you
Yeah,
have a
getting some
license,
kind of
you have
alignment
to
check.
consult it. You have to have a license. Hand off your services to the public, just as an engineer.
Those are gonna have to be surface,
without
it's not
license.
gonna be through the wall. where the-
I tell them, if you do it now, get your fundamentals out of the way, well, you know it.
They have a
Because
slot
I
in
guarantee
it.
you in 4 years, when you go back and look at that physics book, or in 8
So
years,
what's on
when
the
you go back and
inside?
look at the physics book,
Yeah.
you're gonna
I
go,
just obviously on.
I used to know
So
what
it's
that
not, it's not
meant.
going.
Yes, I pulled one
There's
line
not a
out,
structure on it,
I
so
was,
you
I
just
moved
have
here
a
a few
slot
years
just
ago,
to align
and
it.
pulled one
Slots
line,
to just align
because
them,
the key
have a
first
little bit
turbo
more
goes
glue
out.
to support them.
At 43 years old. I know what it means, but, yeah, so anyway, I'm just, yeah.
See, I'm laughing too.
Full scale, what's up? There's no space on the inside of that too.
You will, and yeah, it's so funny, because when you know, it's so in your brain when you first get out, and you just, you know it, and then it becomes intrinsic, you just know it's part of what we do. But yeah, when you got to prove it on the fundamental standard, when you got, yes, I have actually, I know how to do the work of that, but then you just apply it. And the whole thing is good about getting out of school, I remember this took forever to be able to study,
Oh, yeah.
the whole thing. It's a very good job, right? Thank you. Jackie Chestnut, pleasure to meet you, yeah. Yeah, so, and have y'all already gone looking for jobs? Where y'all? Where? Okay, okay. And what are you gonna do?
Being a rotational program, so I'm like looking at everything.
Okay, so you're gonna look at what engineering is? Cause I spent all my time in engineering, cause I love engineering, and you can go into manufacturing, you can go into management, which I hate, and honey, if you wanna run children all day long, but I never liked running children. If I wanted children, I'd have children, and running a bunch of men around and boys and children is like managing children, so, very good. Then you'll be a perfect manager, so, anyway, for those of us that like doing engineering, and what's interesting is nowadays in industry, there are two ladders. There's a technical ladder and a managerial ladder. You don't have to only go through management to be considered whatever, because technically I always say, you have to be management, whatever. Well, now they've got technical ladders for us people that like to say technical and do the engineering, they're equivalent, which are really cool. A lot of your major corporations like J&J do that now. But yeah.
The next group,
Yes, sir.
there's 2 persons is still there from now.
Oh, good. Did they do, now you're again, I'm old school, 40 years, did they do the same there when they come on campus? And then, well, they used to bring like thousands on campus, they never fight all over the place, run you around and all that.
More so
Yeah, we're almost there. Cause I was at UT also, so we did that, yeah, that was, but anyway, no, Johnson, you're kidding, I love working, I retired from Johnson, one of the best corporations you'll ever work for. Awesome corporation, I worked for Alcoa Aluminum and Avgas and Mobil. And they're all.
You touched a number of different industries.
Yes, sir, I did aluminum smelting when I first got out of college, I loved it. I went to work at Alcoa Aluminum in Rockdale, Texas, which is still there. It's the largest smelting plant in the free world. 1.8 million pounds of aluminum per day are produced. And what we produced out of that facility are 30-foot long ingots with the most giant equipment you've ever seen in your entire life. Solid ingots, they're 30-foot long, 2 foot by 3 foot, and those then go to rolling mills. And we then take the aluminum and roll it out to all the things, roll them like foil and all that stuff. And then we made 3/8" diameter rod, and that would be taken to other facilities in the, rolling mills. They take the great big ingots in there, they roll these things out. Yeah, and then I worked at, Mobile Chemical in Shawnee, Oklahoma, making polypropylene manufacturing, which makes film, you know, the film you wrap Oreo cookies in? Snickers bars, Oreo cookies, okay, we manufacture that polypropylene film, and it starts out as raw product, oil, pellets, and all the stuff that you use to get baked, and then it goes into a melting process, and then it goes into great big ovens, and they take this big film and they stretch it out, and then you cut it with different things, and you split it. It's really cool, yeah. So there's just all kinds of neat, if you like fun, like, yeah. Mobile chemical, mobile oil. They have a mobile chemical division that's polypropylene because it's oil. And polypropylene is just simply oil and chemicals.
We produce all of these, we produce all of the, what's it called? Outcomes of oil,
Yes. No, it's fascinating. Mobile's into whole, I didn't even, they make lots of different things with polypropylene. It's funny, when I worked for Mobile, making polypropylene manufacturing, I got to go do, like, we did the Fritos wrappings. So you get to go to Frito companies and Oreo cookie wrappings and some different things like that. And they do all kinds of things. So they also do the recycling of polypropylene, so I learned how to use plastic recycling is fascinating. And I learned how to use all the polypropylene plastic recycling. One of my, I got patents. I really want to do it.
Just gives you back.
Plastic recycling. So that's kind of my thing is plastic. Plastic is the one product we need to recycle.
Right.
I always do that over
It's the first product ever created by man that is not like computer. Wood, will, steel, will, also, paper, all these other products, glass, silicone, break it up, but oil and chemical that makes plastic will not break down
He said he was supposed to.
over time. You know, we may eventually as we put chemicals into it, but it doesn't now.
Yeah, but I mean, it's-
And it also, it just makes sense because it's
We're
always.
supposed to let him know.
Yeah, it's free,
What's
so,
the-
yeah, so, anyway. Yeah, you believe me, y'all got lots of fun ahead of you.
Thank you so much for the good questions.
Yeah, oh, and I love, yeah, cause I love it, and I love the engineering and all the. Yeah. I love your y'all. I love that we started this engineering school here, cause I've been here a long time. We only have things to Texas Tech. Pisses me off, but, you know,
You believe Burner Orange?
well, let's see, well, I graduated from UT, my brother graduated from A&M. He's all right, so get.
We're talking about this morning. You never agree on that. We said what we're doing and then we all dispersed. I guess we're like, yeah, you can tell me. I've gotten your reputation. You go after it.
All right. Thank you all. Enjoyed it. Yeah.
No. Well, mechanics, yeah, civil's on the next one. I'm civil.
How you doing? Nervous yet? You should be.
I'll do next. So I've.
Was he student? Yes. Oh, that's good.
No, I'm the old guy in the class. but
That's
it's all
right,
right.
I was a non-traditional, I get it, so, yeah, so, good for you. So what made you decide to come?
I can't do what I used to do, so I used to do a lot of labor, and I'm also a cabin maker. And I have kind of realized that I'm not gonna be able to do that forever, so I was looking at relations.
I love cabin maker, I just had my house all around, and I got natural cabins, my cabin maker, there's a kid.
Well, the problem is most people don't think it's.
That's the problem, and I know this, cause I just look at my home, I said, I wouldn't.
If y'all would find your seats, we're about ready to start the next presentation.
Anyway, but I was very much, I'm not into the instructor, and I'm chatting for things like this.
I'll send you.
Well, and the thing is that people change, they wanna remodel every couple of years, where it used to be when you would do that, you would, in the old days, your picture was just a room, and you would put furniture in. Nowadays, you know, people just wanna rip it out and start all over again, so they don't wanna pay tons of money for it anymore.
Yeah, there's only three of us. I've been having, like, hot fire.
Yeah, I don't think you have to hop around.
I wasn't sure if they were gonna be rotating back and forth, or if they were all staying up there the whole time. So then
There's only three of us.
I moved around. So I think right there I have you in the screen. Thanks. Stevie and Eric, you're gonna be over on that side?
I'm a no.
Yeah, I was like, uh-oh, broke it.
Yes, ma'am.
So, welcome back. Now we're gonna start the second presentation for the AMI group. The team is Terraform, and they're going to present their project, which is van wall mechanization. With that, I'm gonna leave it to you.
Hello, my name is Jody Hicks, and I'm the team leader for Team Terraform, and these are my colleagues, Eric Chrisman and Steve Guzman. Our project, our client was Dr. Kitch here in Angelo State, and so our device was built and designed for the lab use here at Angelo State. So here, we're gonna start with the general scope of our project.
So to encapsulate the entirety of the project, I know it's a bit of a run-on, but I think it's apt. So the scope of this project is to develop a device that utilizes the rammed earth method to create walls or wall-like structures in order to reduce labor costs, minimize ergonomic risks, and eliminate deficiencies in the construction process. All of this to fully take advantage of the sustainability of rammed earth as a building material into the future.
So here, we're gonna have an introduction to rammed earth.
So what exactly is rammed earth? Rammed earth is a form of unbaked earthen construction in which the soil is compacted into a formwork. Oh, I'm sorry. So the damp mixture of subsoil is compacted into the formwork, and as this happens, the spaces between the particles become smaller and smaller until essentially creating like a man-made sedimentary rock. Rammed earth is strong, environmentally sustainable, and has excellent thermal properties such as a high specific heat capacity. So this means that rammed earth is capable of holding a large amount of thermal energy with a minimal increase in temperature. Rammed earth has been used for thousands of years all around the world in basically every region, every climate. Rammed earth was used to construct in the early construction of the Great Wall of China around 4000 BC. And another ancient example of rammed earth being used as a construction material is in this Moroccan fortress known as Kasbah. This was built in the 11th century and it is still standing today. So now that we kind of know what rammed earth is and a little bit of the history behind it, we can now discuss the process of rammed earth construction as a modern construction material, or modern construction method. So there's 5 main parts to the process, the first part being the formwork construction, and then moisture control of the material, and then adding material to the formwork at specific layer heights, and then compaction of this material inside of the formwork, and then repeating steps 2 through 4 until the desired height of the wall is reached.
So the most important part of the rammed earth construction process is the formwork. If you don't have a strong enough formwork to retain the soil, then it will crumble and you will not be able to successfully complete the wall. So in order to begin construction of formwork must be laid for the material. This formwork is typically either prefab and made out of steel and a composition of wood. So you would have wood sides with a steel backing to make sure that you're able to withstand the lateral force of the soil. And then one of the other important aspects about rammed earth is the moisture content and the consistency of the soil. So the material needs to be at least 30% of clay, and the rest of it can be a mixture of sands or things like that. You typically would have a moisture content of 9 to 11%. Now that seems kind of low, but as you see further on when we get to that portion, it actually makes a huge difference in how well the brick will be tamped.
So the actual compaction process is pretty straightforward. It's a little bit violent. As you can see here, Eric has a pneumatic tamper in his hands, and it shakes you around a little bit, but interestingly enough, even though he'd never used this piece of equipment before, within about 30 minutes, he was well on his way and tamping the brick, like it wasn't a big deal. So we're confident that any student in the lab will be able to learn how to use the tamper and tamper themselves a brick.
So now we go into our brainstorming phase. So when we started this, Dr. Kitch brought us this idea of a cherry picker design that he had seen in a YouTube video, and we're like, man, that's pretty cool. I wonder if we can replicate that. Well, upon studying that, we realized that the form work is lifted in the air, and you use a vibrating plate to tamp the brick inside of it. So basically, you would do layer by layer, slowly rising up into the air. Now, this way of building these walls actually come with a lot of risk. You're having the weight of the machine suspended 10 foot in the air, and only by a cable that's being dragged by a cane. So you're more likely to tip it over and knock the wall off the formwork.
So for design two, this is simply an iteration of the first design, except for this one, this unit is gonna be lifted by hydraulic rams on the base of the formwork. And for this machine, it's gonna transverse down the length of the wall, so once you reach your desired height, after it's finished the compaction process, it's gonna move over on tracks and then decompress down and restart the process.
So after we discovered in both of those methods that having the formwork itself suspended in the air was not pragmatic, so we decided, why not just build a brick on the ground? So we decided to come over and design this after talking to experts at De La Tierra. They were a construction company that's been in the business for over 20 years. And we asked them, hey, would it be better for y'all to use bricks or do it how y'all typically do it now? And they said, architect will go wild with bricks. So that's where we shifted our focus to.
Right. And so after consulting with De La Tierra and understanding that the unitized block method was probably something that was more feasible in terms of their operation and how they do business, actually just adding on to their bag of tricks, actually, so to speak, we came up with this design. So this is created in CAD, and so after speaking with them, we placed an emphasis specifically on the formwork of the machine, because that is actually the portion that is a bit of a bottleneck in their construction process. So they were like, look, your whole design is great, but realistically speaking, we already have the supporting systems, the supporting equipment in place to work with something like a mechanized formwork, just to reduce the turnaround time from brick to brick. And so it would speed up their operation and reduce that bottleneck. So what you see here is sort of a full render of kind of what we built here.
So now we'll go on to the prototype design.
And so, again, we have a kind of overall system breakdown of the machine. Number one being the subframe or the base. Obviously at the bottom, you've got to build the machine onto something. Number two, we have the compaction formwork. This is actually the heart and soul of the machine where all the work takes place. Number three, the formwork relief, which is on the right-hand side over there, and it's actually used to break open after the brick has been tamped, and that is just to release any excess friction that's applying to the outer wall. So this wall that is on this side would actually be like your exterior wall on the structure that you're building, so you want to have as pristine of a finish on at least one side of the brick as you can possibly obtain. Number four being our brick extractor at the rear. So those are hydraulic rams back there, and then they push on a plate that pushes the brick out of the machine so that you have a brick, you don't have to reach in there and do anything, it'll bring it out for you. Number five is the door mechanism itself, and that is obviously a very important part. It's what's keeping all that force in and keeping the dirt from spilling out to the front. And all of these systems work together, as we'll see, to achieve our finished result.
So for the subframe and the formwork, the subframe, picture right here in the bottom left of the slide, is going to provide structural support for static and dynamic loads of the machine. It's going to also serve as mounting points for our hydraulic cylinder rams, as well as mounting points for the formwork relief mechanism that we will get more into detail in later slides. But the subframe also includes the permanent in-place formwork. So like Steve said, the formwork is going to be where the compaction is going to be taking place, and it's going to provide form geometry for the soil compaction. So here we have the soil compaction calculations. It's important to note that compaction in the formwork increases the stresses applied along the walls of the formwork, particularly when the walls have a high resistance to movement. So in order to calculate our lateral earth pressure, that's of our most primary concern as engineers, because we want to be able to figure out how much deformation is in the walls of our formwork. So important variables were needed to be defined, such as the unit weight of the rammed earth brick, the fully tamped rammed earth brick, which is 125 pound per cubic foot. The soil friction angle has been defined in geotechnical tables for the soil consistency that we're using, which is like a clay sand mixture. So the minimum and maximum soil friction angle used for these calculations is 30 and 40 degrees. So using these values, we can then calculate the passive earth pressure coefficient, which is going to be used for later calculations. So the passive earth pressure coefficient for 30 degrees and 40 degrees is 3 and 4.6 respectively. So the vertical effective pressure is the pressure on the base of the formwork. So once we calculate this with the use of equation 2, we can find that the vertical effective pressure is 615 pound per square foot and 559 pound per square foot. And lastly, when we're calculating the lateral earth pressure, which is the horizontal effective stress on the walls of the formwork, we find that the max lateral earth pressure is 2,587 pound per square foot. So using this value, we can then do a deformation analysis through SolidWorks to figure out how much deformation is in our system, in our design, so that we can figure out if it's a good option or not. So here we have the displacement analysis. This was conducted in SolidWorks, like I said, using the max lateral pressure demonstrated, which was 2,587 pound per square foot. And it was found that our max displacement was 0.005 inches.
Okay, so then, so moving on to the brick extraction portion, you know, this is obviously the moving part of the machine, so we want to simulate that and make sure that everything's good there. And so, you know, it removes the ram earth brick from the machine formwork via hydraulic cylinders, obviously right here. And so what you see right here is just a deformation simulation performed with a load that we know is going to be applied to the brick. Actually, we double or even triple the load in some of our simulations to really make sure that we wouldn't see any deformation. And at the highest loads applied, which was actually about 2,700 pounds of force, we see a deformation of about 2.94 times 10 to the negative 4 millimeters. And you know, the extraction plate, everything on the machine is actually constructed with 3/8 inch thick steel, you know, so not very surprising, you know, that a load actually as small as 2,700 pound force wouldn't really move it much. So with this, we established, okay, so we can work with these numbers, and you know, this part is not going to fail on us in any, you know, load capacity, you know, during operation. And so, you know, again, touching the brick extraction topic, you know, we wanted to determine what kind of forces were going to be at work at the brick, you know, what kind of force you need to break over the brick to get it moving. And so, you know, we use the simple equations, F equals ma, and then we can determine a friction force necessary. So when we know that the weight of our brick is roughly around 284 pounds, and we incorporate the coefficient of frictions for steel, because it's steel on steel contact, you know, we can determine that we need a static force of about 200, there's a static force that needs to be overcome about 228 pounds. And so we need to apply a kinetic force of about 137 pounds to actually get the brick moving and get it moving out of the formwork.
So now we're going to discuss what the door mechanism is. So the door mechanism is the latch and its corresponding holders. So we utilized a 4-link locking mechanism. So basically you would just break the top of this arm over and it would lift it out. It would just pick it up here. So we demonstrated on using Fusion 360 a displacement analysis of the door and the force applied, assuming that the latch itself would be completely fixed where the embossments are. And in doing that, we found a displacement of 0.01 millimeters. And here we did a displacement analysis of the billet latches as well. And so we found that the overall force applied on the door by the soil was 2.7 kips. So we split that between the two billet latches, and we found out that at a maximum displacement of 0.007 millimeters. And then we also did a link deformation analysis, and it's same thing as well. We split the force applied between both of these links, or ears on the link, and we found that it was 0.06 millimeters.
So we're going to touch here the formwork relief version 1. So this actually didn't make it to the machine, but we think it's important to highlight because it kind of encompassed quite a bit of time while we were working on the project, trying to figure out what was the best way to go about opening the formwork. And we, you know, had sort of simple ideas, and this is a more complicated version. And so this design features a tooth lockout bar mechanism with mechanical advantage gearing. You can see kind of how it looked laid up on the formwork right there. And so something like this, you know, you could probably put a manual lever on it, or you would put, you know, actuators on it so that when you pressed a button, the gearing could roll over and it would pop this latch, and then the formwork would be able to release, and then you would have some pistons there to catch it and hold the weight, and you would just bring it back into place. and it would lock up. And then we found trying to actually build a thing that in terms of complexity, it probably wasn't worth any gain considering we just needed to open the formwork just a little bit. So we decided to incorporate this to show you part of the process and the design and kind of all the trouble we went through to get to this idea, only for it to be scrapped in the end and, you know, exchanged for something that is much more simple and we think more effective. And so here it is, the formwork, really the final iteration of that. So this is what it looks like, and it's literally just a lockout bar mechanism. So when you pull up on this handle right here, you get this action, this movement. And so this is your side of your formwork right here, and it just opens up with a simple pull right here, vertical pull. So the student can stand off to the side, pull up on it, and the thing will break over without much effort at all. Now this is after you've opened the door, so there is a bit of an order of operations to the machine, but this is the relief mechanism that we ultimately decided upon, and you can see how much more simple it is than the first design, and we think it's more effective as well, so it's an interesting development. And so as far as the formwork is concerned, we obviously had to calculate, as Jody mentioned earlier, what kind of force was up there. So this is just done with static load analysis, and we could determine here, this is just Jody's hand-drawn diagram right here. And, you know, this is where we came up with the number for 2.73 kips when we observed his pressure. So this actual point right here is an important thing because we determined through static load analysis that if we were to go with that locking lever design, each ear would see about 900 PSI. So that's actually a pretty substantial amount of pressure that we'd have to overcome, and it's kind of part of why we decided to change our design once we understood what kind of forces were really acting at the top of the formwork where all that actuation needs to be happening.
So here we had the cost breakdown. So we took every subsection of our design and itemized it so we could better have a total cost idea to then pitch to our client. So we ended up figuring out it would cost $3,600 to build our prototype, and we had a $400 contingency. So we ended up requesting $4,000 for our budget, and as you can see, we were below budget. So along with designing a machine that goes in the lab and you're going to be used with lab risk, so there's a lot of risk and safety that needs to be thought about and implemented. So we decided what areas were more important for us to focus our efforts on. So things that are at risk are your shoulders, arms and back, and ears while using the pneumatic tamper. And then the specific hazards of the device itself are the pinch points, crush points, high pressure lines from the hydraulic unit, and respiration due to the dust particles being in the air.
And so, as Jody just prefaced, we have to make all these safety considerations and kind of come up with a roadmap about how we implement those sorts of safety measures and how we incorporate those into our design. So the first big thing is, you know, validation of our design, making sure that it will actually perform as intended. And so we want to obviously establish and check the functionality of our machine. We want to make sure that the mechanical components of the system are sound and they function the way they should, that they're not going to do anything weird on us. So we have a couple of figures here. You know, we wanted to see this much displacement at the top of the formwork and this much at the bottom. So 2 inches at the top and 0.2 inches at the bottom. And we also wanted to assess the performance and the reliability of the machine. How does the system perform under various loads? You know, is it going to be robust enough for what we need it to do? Is it going to give out on us at an unexpected point? So we want to make sure that all the fasteners will remain tight and in place after cyclic loading and after some of the vibration and stuff like that. We also want to assess the overall durability of the system based on the material properties. You know, can it withstand the moisture of the soil? Can it withstand the grit of the dirt on the formwork without wearing away too soon? Quality control, you know, surface finish of the brick, you know, the density of the brick. Can we maintain the dimensional control that we want out of the brick? So these are all big points of interest or concern during the design process. And so then we're going to kind of continue. So the next thing that we had to concern ourselves with is safety, right? Do we need indicator lamps? Do we need switches? You know, what safety procedures or labels do we need to put on the machine in order to make sure that nobody hurts themselves during operation of the machine? And then lastly, maintenance. You know, what would the maintenance cycles look like? What would the periods be? how rigorous would the maintenance regime for a machine like this be, right? And, you know, we really, when you look into it, there's not a whole lot of equipment out there that's like this at all. So we really had to kind of start from the ground up and be careful in our considerations during the validation process for our design.
So now we're gonna roll into the construction phase.
Before prototyping began for this project, we did conduct a fall task breakdown so that we could manage our tasks more efficiently and meet our project deliverables, such as this presentation today. So at the end of last semester, we did get our prototype approved by our client, Dr. Kitch, and we ordered our materials so that at the end of last semester, so that we had the entire summer to receive this material and start construction in August. So we did start with the subframe of the prototype, since that is the base of it, and everything, all of our components are going to be on top of the subframe. So we did start with that, and then we began with the formwork and the extraction plate. I think we'll go into more detail on this during the construction phase. So here we have the subframe. The subframe we used for this project was actually an air compressor stand that was in the back of the Hunter Strain Engineering Lab. So we decided to use this for the prototype so that it would reduce costs and the time of manufacturing for us. And we do have, we'll go back to it. And we do have these square tubing members on the back of the subframe there that is going to provide mounting places for the hydraulic cylinder rams.
And so after we got the subframe built, we needed a way to move it around the shop. So we implemented these casters that were gusseted on plates. So each one of these casters was rated at 400 pounds apiece. So by adding 4 of them, we can effectively hold and move 1,600 pounds worth of material / metal that's on this device. We bought these casters in particular because they have rubber padding on the bottom, so it would reduce the fatigue of the machine during the tamping process. So you could set those feet down and it would actually reduce some of the vibration on the concrete floor. And then we moved on to the formwork. So the formwork, we took and designed all these in CAD, and we used the CNC plasma table there in the lab. David was gracious enough to teach us how to read G-code and create G-code so that we were able to use all the machines that is available to us as students. In doing that, we were able to get completely symmetrical and repeatable parts. So there's 10 ribs on the full design. So if we had to make those 10 repetitive times by hand, the odds of all 10 being the exact same or slim to none. So this made our manufacturing process a lot more safer and more durable. And here it is continued. We started with one side here, and this side actually has the base of it attached to it. So we had to weld kind of one at a time and then split them in 4 sections to reduce the amount of warpage in the flat plate. That way we can keep that dimensional restraint that we needed for the brick.
And so here, as discussed earlier, we have the extraction plate, which is on the far right over there, and it's, you know, again, designed in CAD, and then we simulated it, and we again use a CNC and all of the supporting equipment we need to cut the pieces, and then we welded them up, and you know, we machined some pins out of rebar, which is strong structural steel, so it has a high shear strength. And so these are the pins that now live inside of the extraction plate where the hydraulics actually mate to the machine. And so here you actually see the pins in the extraction plate set up in the formwork, and this is how the machine currently lives today.
And so now we're moving on to the door construction. And so the key aspect to the door being able to function is whether or not the latch mechanism would be machined both symmetrically and efficiently. So we created the CAD design and mocked it up with a 3D printer. And so we made sure that we did have the correct amount of clearance for both latches, and we could fit them up while we were making them out of metal. So we then took the CNC mill and milled out a piece of aluminum, or 2 pieces of aluminum, and we replaced the 3D printed pieces with aluminum on the formwork. And then we returned back over to the CNC plasma table and cut out all the links that we needed to build the latching mechanism.
And so here you can see an image of the formwork relief. Again, just a bar with two billet aluminum members in here, so these are 1 by 1 inch aluminum square tubing, solid stock. And then you have some steel tubing, and all the user has to come do is grab that top handle, lift straight up, and the bars will break over, and then the formwork will collapse a certain distance. And then with a simple downward appliance of pressure, it will close again. And there you can actually see how much actuation we really get on the opening side, and more of a detailed image of what the actual formwork relief bar is doing during operation. Now, an important part of this machine is getting the brick out, because if you push a brick out and there's nothing supporting the brick, well, the brick could fall apart on the way out of the machine. So we knew we needed an insert. And so the inserts, say this machine was, commercialized, you would have a certain machine like this, and you would have, 20 inserts. And so you would put an insert into the formwork, tamp a brick, go through the process of extracting the brick, and then that brick would then live on that insert for the next 48 to 72 hours. Now, when you move that brick away, you would immediately turn around, put a new insert in, and then you could resume the process of tamping bricks. So as many as you can get out in a day is, we would say, well, maybe buy that many inserts or have that many inserts, and that way you have a continuous cycle going, and then you'd have tamping days and then bricklaying days. And so the insert just serves to store the bricks and move them around while they're in their curing phase.
So this top finish control tool is pretty much just a tool to smooth off the top of the rammed earth brick once it is completely tamped. This was something that Dr. Kitch said that he wanted to include in this project, so we decided to include it. It's pretty much just some bar grading and some angle iron all welded together, so that all the loose material on the top of the brick can be scraped off once the brick is complete.
And this is our finished prototype. So as you can see, we had to include all the safety badges that would be needed in the lab. So some of these include our pinch points, our crush hazards, high pressure hose lines, things like not a step so people don't climb on the back of it. And now we'll go into our safety.
So before building this prototype, we did sit down together and we identified and evaluated all the potential risks that may be associated with the operation of this project. So, as you can see, most of our risks do lie in the very low to low risk. However, the ones that lie in the medium are risks that we decided to mitigate through engineering solutions as much as we could. Like for example, risk number 3, this was an amputation of the fingers due to extraction ram movement. However, this is unlikely to occur, which is not likely to occur in a normal circumstance. It's something that we definitely considered because it could happen. So the way we can mitigate this is through an indicator lamp for when the extraction is ready and whenever the extraction is in operation. We can incorporate a kill switch as well as warning labels. And we also incorporated solenoids into the design so that once the kill switch is activated, the hydraulics will stop. And here's an example of that. So whenever the limit switch is, this limit switch is a normally open switch, so that whenever the whenever the door makes contact with this limit switch, it is telling the solenoids that they are closed. So if the user tried to extract the brick with the door closed, the solenoids would not allow the circulation of fluid to go through the hydraulic rams. However, when the door is open and you press the extraction button to extract the rammed earth brick, then the solenoids will be in their open position, allowing the fluid to circulate through to push out the rammed earth brick.
So now we'll go into the testing phase. So the first thing we wanted to test was the insert. When you start tamping a brick, the insert is basically exposed until you add all the soil on it. So we wanted to make sure that the shear force of the pneumatic tamper wouldn't bend or deform the insert. So we set up this mechanical deflection gauge, and we videoed it in slow motion to get our maximum deflection value. So as you can see here, it deflected 0.003 inches of elastic deformation. So that means it went back to its original state after the force was removed. Therefore, we could validate that our insert was of the correct thickness and it would last through our tamping process. Secondly, we went and we attached strain gauges to the formwork. So through our simulations, we were able to identify places of high stress and strain locations. So we applied a sensor in 4 of those places in between each of the ribs. And so as you can see here, our maximum value was down here on the relief side. It was 286 microstrain. So we then took that value and we were able to go into our stress calculations.
Right, where we use
Well,
the,
the max strain was 672.
Oh, my bad.
Yeah.
672.
yeah.
And that's channel 3
Fine.
instance 4.
Yeah, and actually during the testing process, you know, we lost a strain gauge just because it is a pretty violent procedure, you know, with the tamping going on. So we were actually lucky that 3 of them managed to survive. And so, and actually, kind of to touch on that before I go into this, you know, the formwork relief side is not as fixed as the fixed side, so it would make sense that we would see the most strain there. And so when we use a modulus of elasticity for the steel that we acquired, which is about 29 times 10 to the 6 PSI, we can then do some calculations and we determine a max stress of 19.48 PSI. And across the area that we have, this equates to a force of about 5,600 pound force. And that is applied laterally by the earth after the tamping process has been complete. So this is actually at maximum height of the brick, fully tamped. So this is static load at that point after the brick has been tamped. So getting a little bit more into the testing and figuring out, you know, what works, we have to consider the brick composition. And this is kind of the more artisan component of the entire way of doing things. You know, every company, every guy who's ever tamped a brick or they do this professionally, they all give you a different answer for what their optimal or ideal composition is for a brick, depending on the soil, the cementizer, and the moisture content. So for our experiment, you know, we decided to go with 5% Portland cement, 40% red arroyo soil, 55% sand, and we prescribed a moisture content of about 10%. And you can see all those things pre-staged on the cart that then go into the mixer, and this is all a very timely process, you know, to make sure that you go from mixed soil to tamp, you know, within a certain time window. So we had to kind of lay everything out the way they do in the field, kind of set everything up, and start the tamping process for our brick using this material.
And here's a video of our operation. Yeah, I think so. So here we're conditioning the soil in the cement mixture. And what I'm adding right now is the Portland cement. So I pre-weighed the bag and I knew what half of it was. We split it into 2 batches so we can more accurately have, because the machine is only weighted for 400 pounds. This is our very scientific way of checking the moisture content. So basically what you would like for the soil to do is ball up, but then the moment you press on it, it dissolves. So that's kind of the moisture content we were chasing for. And as you can see here, it didn't quite stay in the ball, so we added more soil, or not more soil, more moisture. And this part of the process is more like feel as you go.
Right, this part of the process is very difficult to automate. And the guys who do this every day for a living that we talk to, you know, they have a very specific way they do things. And, you know, you can't remove the human component from the process. So we're pouring out our conditioned soil right there. A little bit labor intensive.
And here I'm setting up the machine. So over here, we have our shut-off solenoids. These are the safety solenoids that protects the rest of the machine. So you're gonna hook up your hydraulic hoses to both sides here. There's only one orientation of them, so it makes connecting it easy. Now the unit we're going to be using for this device is the Edwards power unit. So as you can see here, there's the same quick disconnect connectors right there. So I will connect the hoses in the same corresponding manner. And as you can see, it hooks up and disconnects. It's fairly simple. Last step, fairly quickly. Control the extraction of the brick. This controller will be mounted onto the control panel for ease of access. Now, in order to use the unit, you must first make sure that the unit is turned on. And so here, we're dumping the soil in and we will begin tamping. So things like this, for our full overall project, we would have like a conveyor belt filling it in and things like that, trying to take as much of the human input out of it. And that's us finishing the top of the brick.
So now, when the machine has been set up and the hydraulics are running, we can come back over to our machine. And so the first step in getting this brick out of the machine is to first turn on the switch. So here we have our main power switch that is now on and active. The next thing that you'll have to do, because unless you do this, you won't be able to do anything else. So there's an order of operations. We want to get the door open. So as you can see here, we have a fully tamped brick. It's ready to come out. So step one is to open the door. You can see a beautiful finished brick right there. The next step is going to be to activate the formwork relief to release the friction along one side of the brick, and it will reveal to us what the face of the brick looks like. So this is usually the most exciting part. So here, what I'll do is simply pull up and actuate the formwork. Now that we know what the brick looks like, we'll want to actually go ahead and extract it with the hydraulic system, which will be next. Now that the door is open and the formwork has been relieved, we want to actually push the brick out. And so that all happens with the use of this controller right here. So this controller actually operates the Edwards power unit. So we're going to press the white button for forward, and the brick should come out of the formwork and reveal in all its glory what it really looks like. So let's go ahead and do that now. Now I'm retracting the extraction plate. Now we're ready for another brick.
So here is our finished brick. I'll take you around it for a second. As you can see how smooth this side is, no ridges. That's good. A well-defined corner. You can see at the top where it got kind of hard to tamp the top of it. So we have a little bit of breakout there. On the side here, you can see where our strain gauge wires were. So that was expected. That was from the tape, strain gauge wires. Another good corner. This was the back corner where the pneumatic tamper or hydraulic press was at. So as you can see, it kind of ate up when it fell out of the formwork. Same thing here. But all in all, a good quality brick.
Said they were having this problem. No, just the next one. Should be. Yep. All right, and this is our finished ram earth brick.
So, all in all, it was a success in building a brick for what our client wanted.
Yeah.
So,
So the top, interestingly enough, so it only actually sat for about 18 to 20 hours before we removed it, because we were kind of excited, so we couldn't wait full 48 hours. And so when we actually took the brick out, what seemed like it was very hard on top was actually still in the process of hardening and curing. So when we took it out, we had a little bit of falling away of some of the soil around the top. But you know, if you were to take it out and set it aside, it would be a beautifully uniform brick once it had time to cure in the sun. It's still not working.
yeah, you're good. So, improvements and considerations. So, the number one thing that we didn't design multiple iterations of was how the door latched on the front. So as you can see here, this latch is actually oriented to the upper half of the door. So that poses problems down here at the bottom. When you're starting to tamp and you have all that force on the bottom, well, it starts to walk to the bottom out. And in hindsight, it's like, oh yeah, no brainer. But anyways, that's how we designed it. So that's how we built it, and we learned from it. So our proposed option of fixing this would be to move the second billet downward. And easy fix, but it's something that we didn't think of in our design. And also thicker or harder bolts. So these links are just bolted together, and we just use the bolts that were in the lab. Well, as you start applying that force on those links, you're starting to torque them over. So you then implement a torsion, and you start getting warped or bent bolts. And that's another thing that allowed the door to kind of creep out a little bit after we were done tamping. So these are some things that we thought of afterwards that we're like, you know what, if I'm gonna do it again, that's something I would change. Thank you. Now,
Thank you.
we would like to open it up for any questions.
Question?
Yes, ma'am.
Y'all said you made the pins out of rebar?
Yes, ma'am. We had 1-inch rebar.
Uh-huh.
They're in the lab, and so we had looked around at like Tractor Supply, places like that, and we could not find a pin that was the same diameter as our hydraulic cylinders. They already have a Heim joint on them, and so we wanted to match that. So all our pieces were cut to the same diameter of the hydraulic cylinder, so we turned them down on the lathe to make our own pins.
And rebar is structural steel again, so it does have high strength.
Actually,
tensile
rebar's
shear.
pretty cheap as steel. so-
Yeah.
That's how it's
Well, it's got good
Yeah.
strength for what we did, and considering the load applied, 200-300 pounds
Yeah.
shared between each pin, it's substantial enough that it did what we needed to do. That, and I just wanted to make a part on the lathe for the.
Well, I get that,
So-
yes.
So, that's part of it. Anybody else? Any other questions? Yes.
So you said that there was like 5,000 something pounds of force that the brick made. Can you explain more what that means and how it works a little bit?
I don't even know what
Keep
slide
going,
it is.
keep going up, down.
I think we're.
It's in testing. It's towards the bottom.
Sorry.
Yeah, sorry, that was a little far back.
No, you're good.
So keep going.
Yeah, keep going. It's in testing.
Here.
Yeah.
So in our calculations, we determined that you would see about 2,500 pounds per square foot. Now, the formwork is actually 2 feet long, and approximately 12 inches tall. So you actually have 2 square feet of area. And so that's actually, we were pleasantly surprised to find through the strain gauge testing that we're actually right in the ballpark in terms of predicting the force that's acting laterally across the formwork. So the strain gauges were placed near the middle, right? So we used the strain measured there, which is where the strain is at the highest, to determine this number. And so, like I said, with Eric's theoretical calculations, we determined that, well, for every square foot, we should see about this much pressure. We know, again, it's 2 square feet. And so this number is actually directly in line with that theoretical number that we came up with when you apply it across a larger face. So,
And another aspect of that is that in the soil calculations, we assume 30 to 40. Now, we don't know the exact material properties of like the red arroyo or the, per se, the sand that we chose. So that friction angle might have been higher or lower. It could have been all the way up to 50. If you look in the geotechnical charts, very dense soils can exert a friction angle of 50 degrees. So those are also things that we just kind of had to take a ballpark guess of, and that in turn.
Yeah, the stresses developed by kneading soil is actually a very interesting problem, and it changes with the shape of the tamping head and all kinds of stuff. It's a very, very problem.
Yes, sir.
So I have two questions related to the other two questions were asked. One is, this max stress of 20 PSI seems really low to me, so is that a tensile stress or is that a bending? So what part of the structure gets that maximum stress, and what is that analysis you did there? Because that seems really low.
What slide to go to for that?
I don't
Yeah,
need a
so
slide.
basically, we put
You
this.
say right here that your maximum stress you experienced in your stress calculation was 20 PSI, so where was that and how did you calculate that?
Okay, so we put the strain gauges in the middle of each rib, which we would know that that's the most unsupported section of that formwork.
So
Is
this
in the
measured
center
on
of the ribs.
On the ribs?
So like if this is a rib and that's a rib, we placed it in the center of it, between each one.
On the ribs or on the facing?
So like if this is the face of our formwork,
Right.
and this is a rib, and that is a rib, we've set it
Okay.
directly in the center of each one.
On the inside or the outside or both?
In the inside.
Okay. Why'd you pick the inside, by the way?
Well, so on the outside, we have bars for torsion, and so in order to put a strain gauge on a device, you have to sand the metal down and then polish it and clean it, so we opted for the inside due to ease of, to get the device
We
on
had just
there.
painted it.
And so,
They didn't survive the,
yeah, and one of them didn't survive a aggressive tamper smacking into the side of it.
Yeah.
okay.
Yes, sir.
So now back to that stress. Now this is a calculated stress, right?
Yes, sir.
Okay. So you calculated that you're only gonna get 19, and this is the maximum
Bending.
stress in bending?
Yes, sir.
Okay.
How big is your brick?
Our brick is 2 foot long, 1 foot wide, and 1 foot deep.
And is that a standard?
So.
Is this, I'm kinda curious about the whole
Yes,
Rambert
ma'am.
brick
Yes,
thing
ma'am.
now.
So brand earth, what they
understand
would,
brand- yeah, I understand
traditionally,
the whole
right now,
thing.
what they would do, let's say this is an 8-foot wall.
Right.
Well, we would set up an 8-foot tall formwork, and we would climb down in it, and then tamp like we
Right.
did there on
We
the
just-
ground.
right.
Yes, ma'am.
Right.
So basically, there isn't a standard size
Okay.
for a brick, and so when we had talked to the professionals at De La Tierra, they basically told us, if you get to, it's 8 foot long and 4 foot tall, we'll tell the architect this is what we got to work with, and the architect will take it over in how to incorporate that brick size into their building.
So traditionally Rambert is like this, but then how do you connect your bricks together?
So these would be like a thin set mortar in between
Okay.
each
Like a
joint. Yes, ma'am.
traditional
And
type?
each brick roughly weighs about 300 pounds.
Okay.
So mostly gravity is holding it in place. So-
But you did some scaling to determine what prototype to do this at?
Yes,
And
yes.
you didn't
So
present
our-
that, but there was a scaling exercise to figure out what prototype.
Yes, and actually we have
You go
some
back to it.
images here near the end of our presentation of, so like in this design, so it was like kind of scaling back, so we had this big picture idea, and then we kind of refined it, well, we don't need this, this is what we need to focus on. So this would have been a 2 foot tall by 4 foot long by 18-inch thick wide brick that would have weighed about 3,200 pounds. Now they have the equipment necessary to actually lift and move this stuff around, and for the speed at which and the efficiency at which they tamp these bricks, this is something that's actually very manageable for them. But for sake of manufacturability, practicality, and safety in the lab, we decided on a half-scale version, and that's what you see achieved in our final design.
So these bricks are currently being used.
So right now, the only way they do modular rammed earth housing is that they would do sections of walls
Right.
in a factory, and then what they would do is take a giant wet saw and cut them, and then ship sections of walls to where they're going to be at. So there's really not a modular
Method of doing
small
that.
form
And
of
in
doing
those
this.
cases, majority of the time, they're actually only making a fascia. And so they're thin sheets that then go applied to conventional walls.
Right.
So not only are you using all of the conventional construction materials that you would in a building, you're also using rammed earth.
Oh.
So it's kind of not exactly the aim of our project, so the aim of this project is increase the sustainability
Sure.
by removing the certain construction materials that we use in conventional home construction, and to create a more, you know, eco-friendly, long-term sustainable, you know, way of creating homes that people could afford into the future. You know, just increase overall sustainability and reduce, more importantly, overall energy consumption.
Sustainability.
Right.
Sustainability of what?
Yeah.
The
Sustainability of
globe. So
what
like,
globe?
no, globe we're on. So,
I'm so.
okay, so right now,
Hold on. Back up.
the way you traditionally build a house is usually.
I know how to build a house, I
Yes,
just built
ma'am.
one.
Yes, ma'am.
But back on sustainability of what?
So for example, rammed earth as a material has excellent thermal properties, so your energy consumption is reduced. And because of its specific heat behavior and stuff like that, the way it retains energy, a typical behavior you see in a lot of rammed earth structures is like if it's cold outside and there's things and people inside, it tends to be warm inside. If it's hot outside, it tends to be cooler inside. So by that, its very nature as a material, you're already automatically reducing the amount of energy you need for climate control. Not only that, rammed earth is fireproof, so your house won't catch on fire. Not only that.
Theoretically.
Yeah, theoretically.
Theoretically.
Assuming you have an aluminum roof and all this kind of stuff.
Yeah, there's a lot
Which
of-
actually, a lot of them do,
Kind of
use
same
modern
thing as
materials.
metal buildings,
So
same
the
thing.
key to this, making sure that it's sustainable, is staying under a 10% Portland cement content.
Okay.
So Portland cement is very inefficient, and sustainability wise to produce. There's a lot of energy that goes into making Portland cement. So if you have this higher, let's say like 15% Portland cement, it's no better than a concrete wall or a cinder block house.
And it's
So
a
if you
fine
keep
balance.
that low and you're able to use soil that's on site, you're not trucking in material. So you're reducing the CO2 emissions that it takes to move the material onto the site. You're also not importing things like wood for your exterior walls, sheetrock, things like that. So your
Fiberglass
exterior
insulation.
walls are all made on site.
I just phoned everything, so.
Yeah, another big thing is
Phone.
And you don't need
insulation.
insulation for your exterior walls because the geothermal properties are so high.
Anyway, I just wondered if the whole sustainability aspect of it versus the other
Yes, ma'am.
traditional.
That really
methods.
has a lot of sustainability benefits when you dive in and study all of it. And it's like, yeah, if we can create an infrastructure for this type of construction, which currently does not
Which-
exist. These guys.
But that
do
whole
this.
infrastructure is not, you have to look at the sustainability
ma'am.
of the infrastructure, because that whole
And,
plays into it
and that's
as
where you
well.
play into whether.
Yeah.
Yes, sir.
So you discussed in your design considerations that you were concerned about the vibration control, the fasteners, and the maintenance schedule, and dimensional control of the brick. So my question is, what were the specifications for dimensional control of the brick, and did you meet those, and how did you analyze vibration and fasteners, and what did you determine about the maintenance schedule, and how did you analyze those things?
So in terms of dimensional control, we wanted to see ideally no more than about 5,000 to 6,000 in or out of the brick face. We actually are within 1,000, so you can't even fit a human.
On every surface but the top.
Yeah, on every surface but the top, which is kind of,
Top
that's
is
the
where-
more, specialized part where you have to tap the brick
Well,
and
your
finish
top's
it
not
by
within
hand.
1,000 for sure.
No.
No.
That's what I'm saying.
And then
Every
after we
dimension
took it
but the
out, it
top.
became like an inch, so.
Yeah.
Yes.
About 1,000th of an inch on every face, so it's actually, if you shine a light on it, it'll actually cast a reflection down on whatever surface it's on. It's very shiny, because it really is really smooth on the surface. In terms of fatigue, vibration, we feel like you could have spent an entire year analyzing.
So my question
different
is,
parts.
did you do any analysis on that?
No, we
did some
took
hand
what
analysis,
we
you know,
looked into
check a
it
thing.
and we realized that this is
So my point is,
outside the
be
scope.
careful about what you present when it's something you didn't really do.
Yes, sir.
Okay.
Yeah.
The same thing with maintenance, right? You didn't really analyze the maintenance.
Well, we have a full maintenance
Yeah, we have a
plan,
user manual.
but we,
Right.
yeah.
But that was done that was not part of the design process, that was
No,
a
it was not.
post-design thing, right?
Yeah, we kind of,
Okay.
we got into it, built the machine, conducted
You
a
just,
couple of
you were
experiments.
overselling something you didn't do.
Yes, sir.
Right. Okay,
And
that's
y'all-
all right. That's all
y'all
right.
said something-
You're better, you're better off in a process, look at, these are considered, these were not part of our scope.
Yeah.
That's all fine.
Right.
But you
Yes.
gave us the impression that that was in your design process, which
Yes.
it wasn't, right?
And I love how y'all did the initial different locking down methods on it, on that too. And then you said you realized, because the old theorem is the KISS theorem, right? KISS, keep it simple, stupid, and we all have to, yeah, because it's amazing. And I love that y'all did that, and then you said,
And actually, that ethos is carried across kind
Yes.
of the entire design of the machine.
Yeah, I love
And
that.
just because we realize that our machine is, is a technical device that students will probably use, so we need to, one, do a good job of it, make sure nobody's gonna get hurt,
right,
and make it easy enough to use for everybody. So those were kind of leading, north stars, if you would, throughout the design, and particularly the building phase of the project, which consumed the entire semester in our case. It was a tedious process.
What, you switched to aluminum for two of your parts, and what was the rationale for that? The door latches,
So-
or the door latches and part of the release mechanism was
On things
aluminum?
like the latch and stuff, it's easier for our CNC machine. All our bits that we have bought are all designed for aluminum because it's a softer material than steel.
Okay.
So that's kind of the tools that we had on hand, and so that's why we
How'd you
went that
attach
way.
that to the steel?
And we simulated
Oh, we
that.
bolted it.
Yeah,
It's
and so we
bolted.
said, well, the aluminum's what we have, our tooling will work aluminum easily.
That's fine. What
Let's
about
simulate
what about
that.
on the release mechanism? How come you should use a different square tube, steel tube? What
So
did you- what use?
aluminum square bar that's completely solid is cheaper than steel bar that's the same one by one. I
We also
believe.
had to mill a latch.
Yeah, and we also had to mill it down so it fit inside of the square tube.
The 1 inch, cause it's not,
Okay.
it may be 1 inch square tubing, but internally it's not exactly an inch, so we had to machine some small stuff.
Yes.
On the latches, do you think it would have been better to make those out of steel?
If we had the proper tooling, yes.
Yeah, yeah,
That's
because
interesting.
steel on aluminum is obviously not ideal.
Yeah,
You
so
know,
the steel will wear away the
Yeah.
aluminum.
But the latch is, it's not like, yeah, it sees some abuse, but it pops open and rolls itself out pretty easily. So for like the prototype, it's actually, it works decently enough, so we're like, okay, we were okay with this, and we didn't feel the need to revisit it for now.
Yes,
Yes,
sir.
Dr.
Can you describe the curing process?
So basically what you would do, so the way they do it now is when they tamp a wall, they leave the formwork altogether for 2 days and then they come back and tear it down. So our curing process would be just us ejecting it out of this, and so the soil itself is uncured. That's why we have the formwork, so if you scoop it up and move it, it's not gonna fall apart
The insert.
because all the forces took in from the insert and you're not applying that force onto the brick. So basically, it's just sun-baked cured, kind of. You just set it out. We didn't put it in like a curing room or anything like that. It's just letting the moisture dissolve out of it.
It's not dissolving, by the way.
Yeah,
Yeah.
and dissipate. Bigger word.
You didn't have a geotechnical consultant to help you with the mix design, did you?
Actually, we did.
Oh, yeah.
He told us we got it wrong, and then we fixed it, and it worked out. And that guy was you.
Pretty sure that's not right, because, do you know what the composition of, red arroyo soil is in terms of clay and sand?
The red arroyo itself?
Yeah.
Well, we kind of just used the red
No, I do
arroyo
not.
as.
And I'm
as
questioning,
a-
you
I
know, you know the,
No.
and there's no reason you would.
No,
No,
right?
no,
No.
we did not
Right.
ask about that.
So it's about 60% silt and sand.
Okay.
So,
The red arroyo itself.
yeah, so there was no I mean.
Yeah.
So this is a comment about getting the right people to help you out with something, cause,
Yes, sir.
in fact, when you were mixing, I was trying to figure out why your soil was so sandy that you're using there, cause I wasn't there when you mixed it, and I didn't realize that you'd added sand, because you should have just used the red arroyo soil by itself,
Mhm.
would have been just about right. So, my point is, you know, make sure you get, and you know, you guys are
Yeah, we
not
didn't take-
geotechnical engineers, so you're not expected to
Yes,
know
sir.
that, but because you didn't ask somebody at the right time,
Yep.
you have the wrong material that you used, you used the wrong material for the.
I'm glad to know that, cause we were actually gonna get closer to 70% sand at first, and we actually dialed that back.
Yeah,
So
good thing,
in a way,
because-
we kind of mitigated.
So
that.
now we're at kind of
Yeah,
70.
when you were
Yeah.
mixing it, and I
Yeah.
was over there for the few minutes, I was like, I don't understand why this is so sandy, where did you get this red arroyo soil from? Cause like, and it varies from place to place,
Yeah.
but that's because you added a bunch of sand to it,
Yeah.
yeah,
Yes,
that
sir.
was.
so that, so is this something like you build these in the area that you're at using the soils that you have?
That's
It's
the
much
Is
more-
idea.
that part of the idea too?
Yeah,
That
so
you-
the-
You take combinations you have there and see how it works?
Yeah, that's one of the things that makes it more sustainable, is you're not trucking materials,
Right.
spending all that fuel to
So-
truck materials. from
So
all
here
over
you
the
may
place.
have a little bit of different variation and then overseas you got a little different, and that's how you, and then you work with that to get your brick.
Absolutely.
Interesting.
Yeah, part of the design process is to determine what local soils you can use, and the red arroyo soil probably is pretty good just by itself. so.
Yeah, the important thing is you have a clay loam
Right, a
soil,
clay loam.
something that has some adhesiveness to it, so that when it cures, it becomes what we have here.
Yeah,
That-
question.
that's-
Dr. Batch, you had a question?
Yeah, Dr.
What do you recommend for the top surface of this brick?
So, I would recommend that if you don't fill this formwork all the way to the top, and you stop kind of 2 or 3 inches from the top, you're able to actually compact it better. When you get to the top, it likes to throw the soil everywhere. And so you're kind of hesitant to get it everywhere, you're trying to keep the tamper inside the box, and so it kind of makes a mess of it. So I would recommend, like, if you're shooting for a 12-inch brick, if you make your formwork like 14 inches, a little bit higher to give that tamper some room to actually hit the edges, you would have a better top soil, or top consistency.
How could we get it like perfectly flat? Is there some way that, like even then, like you're still
Yeah,
gonna
you
have
can
to
get
stop it,
pretty
and
close.
You're gonna have to like kind of guess at like what's 2 inches and how, like the sides are nice
Yeah.
and.
Correct.
Now, in our
Yeah.
case, when the
So
brick
how
came
do-
out,
How do we get that on top of?
I would think
those
like,
and
so,
improve it that
a
y'all-
solid plate compaction is not good for,
Yes.
the entire process of it, but I do believe you could probably get by with a vibrating top plate at the very end to make sure that the top is fully compact.
and they actually sell them, so they're handholder posts, and it's a square and
Yeah.
not a ball, and it's just a flat face tamper. Now, while that's not good for the tamping process, as Jody said, because during the tamping process, you want to knead the soil, like you would knead dough, right? You don't just hit it, you wanna knead it up. But at the top, you could absolutely use that, and then for that, actually, I'm gonna put this in terms Dr. Kitch may understand. The same reason at job sites, when they're doing actual ground compaction, the big rollers have knurling on them and those
Yes.
studs, and then for when you're finishing a road, they use smooth pave rollers, right? So it's surface control is a little bit different in that way, but it's the same sort of, it's analogous, it's the same thing.
Matt, did you have a question? Okay.
End use, would these be sealed or just exposed to the elements?
So you would have the choice as a homeowner to either plaster it like you would stucco on the outside, or you would have it raw finished like that. The idea is that the cement content on the inside would stabilize the brick and prevent it from wear from the weather.
Right, and don't get us wrong, you know, when these guys, they do this professionally, it looks much more like what you have.
I was gonna say, you can get out of the presentation and just scroll.
I'm trying.
Press escape, yeah,
So, you know, they really do.
and then
look-
make that full screen.
right here, I can't see. You know, so you can get really aesthetic looking walls, and they change the color along each lip, which we didn't do, because we didn't have, what they use are oxidizers of different pigments and stuff like that. Oxides rather, not oxides, or oxides, and then you can add it to each lift or every layer, whatever you want, and you can get these beautiful flowing finishes, you know, that are very aesthetically pleasing.
Are there any examples of them like putting epoxy on it or?
I don't know if you would.
Putting what on it? Like an epoxy or?
Like a
I don't think
sealant?
so. Typically, it's like stucco or something of that.
Something lime, like a lime sealant, yeah, that's usually what they'll use.
Actually, allowing the water transfer in as part of this thermal.
It's important.
Yeah, and in a lot of cases, you know, it's like, why would you wanna cover up such a unique and beautiful finish? So that's kind of why people currently build these homes the way they do. Now, the intensive labor costs and sort of inherent danger of the process kind of lends itself to the higher cost of developing buildings this way right now. So the whole idea, the impetus for the project was, again, to create a device that would reduce some of the bottlenecks in the construction process, like having to have your workers up in the formwork, cart the material all the way up to a formwork from a ground level, and, you know, so on our site visit, we just kind of highlighted, that's a massive inefficiency, so how can we sort of create something to put it all in one space, make it easy for them, safer for them, and sort of increase their productivity through time, and by extension, reduce the cost involved with doing this kind of work. So.
Cecil?
In considering the full scope of your entire project, what would you say the greatest challenge for the team was? What was the most challenging aspect of the project?
So you can have a top-down design, and you know, your design may be excellent on paper. You have the CAD, you have the validation, you have the simulation, you know, and then you make that first cut and you make that first weld, and immediately it doesn't go exactly how you planned. And so throughout the building process, as careful as we tried to be, every step along the way, you have to bridge a small gap. Well, this isn't exactly what we need, so how do we make it perfect? How do we finish it? How do we fit everything together so that the machine actually operates as intended? And it's bridging all of those small little design gaps that you don't see in the design process that really make the difference between something just being an idea or a relic and being a finished and working prototype or machine. And I think that was probably the biggest challenge for us, was overcoming all of the small challenges along the way, so.
How many of those should you have figured out beforehand now that you've done it once?
A good chunk of them probably.
Yeah, well.
It did make the manufacturing process a little bit longer, because like we designed something and like the back that catches the plate, well, we didn't weld it on that good. And so the first time, I didn't have the welder set to the right settings and it ripped the back plate off. So it's like, well, okay, that didn't work. Let's do it again, weld it back on and try again.
You have to break a few eggs to make it up.
So, there's definitely some restraints that kind of came into that.
Any other questions?
So what'd you learn most in the process of doing this? Hope done?
I think we need to pause it unless
Okay.
we're gonna hang out. We have 7 minutes in between our sessions, so.
Well, I guess.
If you have more questions for the team, please feel free to hang out and talk with them. I'm sure they would love to tell you about the project. I mean, I kind of expect, but do you want to stay on schedule?
That's what we just
Push out like 6 by 10.
Part of our family.
There's a one junction that like there's a junction that like you go this is right. So on that junction you go there and like an hour. Like it was like a whole bomb rush, right? Nobody's moving. And then the last time, I mean, I booked now if I go, I just book the work day. It's open. Work days and also we have to avoid 8 to 9 and 45. And do you think, oh no, yeah.
No.
Sure.
Not for Thanksgiving.
Get a picture of the
For Christmas. I don't know. We haven't solidified our plans. But this year for Thanksgiving, I think my dad.
Which one of these guys did you raise? No, we put up with them. I wasn't sure in introduction engineering.
My brother-in-law's family. You did great. Really looking forward to that.
That's right. You know what?
You learn.
The day- we sell the-
Yeah, we should have given.
Different eras, you know.
Yeah, I've never
So.
We'll see you more in the next couple of weeks. Thanks for helping. I don't know what we're gonna do, but thanks for supporting. Really appreciate it. Excellent job, brother.
We've heard a lot about it, not to that extent.
At least maybe online.
Well, how's it going?
I mean, maybe, you know, maybe we have
Look, man. Got it. Oh, I
All right.
He's got, his like proportions are like.
Excited?
So he was giving me some pointers. It felt a lot better. I gotta watch it. And
Somebody had some close around.
I used to think that there was one particular way, you know, everyone either you're gonna be good at it or you're gonna be out there.
I will say that your proportion.
I definitely got a lot of
Bring you all right?
Ford Brown. Yes, sir. I was Ford Brown. Working that day.
Yeah, I just he did anything.
I had to play it. Part of the new arrangement. I guess it's brutal all across the state.
I think that's what we're trying to focus on now. Heavily weighted grade wise compared to anything else.
What's going on, man?
Thank you guys so much for coming.
Hey, what's going on? Great to see you back here.
Got about a year to go. After next semester, I
He said he can't see this. All right, welcome everyone. It's exciting to have everyone here. And so I'm proud to present the team Parks and Rec Engineering. And so they are the senior civil engineering design team for the fall 2022 semester. So it's been my pleasure to get the chance to work with them closely on this project and going through. I can say they are definitely pros at giving presentations. So I think our weekly meetings went very smoothly. I think they're very successful at providing you with the details that you need to hear without the details, the extra details that you know they've done their research, they've done their background, but they kind of just present what you need to hear, and that's especially good when you're a client and you're listening to an engineering team. You want to just really know the important aspects. So I think they will live up to that standard today, and so I hope you enjoy their presentation. Before we get started, I did want to invite Ms. Sylvia Pate up. On behalf of, this is our client, and if you wanted to say a few words.
He's acting like he's afraid of me, so. So I can honestly say these guys have been so fantastic to work with. Their follow through, their commitment, their detail orientation, their communication, I could just go on and on. Having been an executive in big corporate America and the big city previously, I can say I would be happy to have any of these guys on my team. So thank you all so much. They've worked on behalf of City Park, Christoval. I'm head of the nonprofit that is doing the improvements to the park. And what's cool, among the many things that are cool, is that we are actually starting construction of some of the work that they've done. So it's real-time experience. So it's been awesome, and I'm gonna miss you guys.
Thank you, Ms. Sylvia. Thank
Thank you for the opportunity to work with you, and on behalf of the team, I'll pass it over to their team leader, Juan, to introduce the team and talk about the project. So, thank you.
Thank you, Dr. Betts. Let's do it. All right, thank you all so much for being here today. On behalf of Parks and Rec Engineering, we would like to thank our client, Ms. Sylvia Pate, as well as the rest of the board of directors for the Christoval City Park. We'd also like to thank SKG Engineering for providing the survey of the park. We'd like to thank Texas Department of Transportation, as well as the professors here at ASU for answering any questions that we had throughout this project. Without further ado, we'll be presenting our senior capstone design, Christoval City Park. So just a little bit on our team. Dr. Anthony Battistini was our advisor for this course. Each member of the team had the opportunity to lead a specialized team in the project, as well as be a second member of a second specialized team. So just a little bit on the scope of work of the project. We were asked to design a quarter-mile walking trail, which will be going around the perimeter of the park. We'll also be designing a couple of steel structures that will be in the park itself. Also, we will be designing foundations such as square footings and spread footings, which will support these structures. We'll also be providing a pavement design for the existing Christoval Road, which is going down the center of the park. Finally, we will be doing a drainage analysis of both pre and post development of the site, and we will be providing all this in plans to our client. This is just where our project is located. Our project is located 20 miles south of San Angelo in Christoval, Texas. So in order to meet project requirements, we divided up into 6 specialized teams. Each team will primarily be overseeing a specific part of the project. For example, structural team will be doing the design for the structures in the park. The transportation team will be doing the pavement design for this project. So here we have a site layout and an aerial view of the site and what we envision it to look like post-construction. As you're coming off of Texas Loop 110, You will have the option of 8 parking spaces with 1 handicap space. As you're getting off your vehicle, you will be greeted with a walking trail entrance. This entrance will be laid out with pavers. Each paver will have the name of people who contributed to the park. As you're coming down the walking trail, you will be weaving through the beautiful trees of Cristobal City Park. On this southwest end of the park, we will have a small detention pond, which Parks and Rec Engineering has designed in order to discharge runoff, post-development runoff after construction. In this general area right here, we will have a pre-engineered playscape for kids to enjoy. As we continue down the walking trail, there will be a 40 by 40 foot band shell, which is a steel structure that Parks and Rec Engineering has designed. This structure will primarily be for musical events for all Cristobal residents to enjoy. Following the trail to the left-hand side, there will be a family pavilion. This pavilion will primarily be used for recreational use for Cristobal residents to, have cookouts or just have fun on a Sunday there. Finally, as daylight runs out, don't worry, Parks and Rec Engineering has you covered. We have strategically placed 16 lights throughout the park in order to continue the fun at Cristobal City Park. Last but not least, down the center of the park, we'll be providing an upgrade to the already existing road. And this concludes the site layout. I will now pass it on to Seth with the hydrology and hydraulics team.
Good afternoon, everyone. My name's Seth. I got the opportunity to be the team lead for the hydro team this year, accompanied with Brian Rodriguez and Juan Vasquez. Just to start out on our scope overview, kind of what we did with the hydro section. So we performed a pre and post-development drainage analysis of the site. The whole goal of doing this was to ensure that the proposed runoff post-development is less than or equal to existing conditions. And this helps prevent excess flow and mitigate the flooding and potential property damage from occurring downstream. Also in this scope, we provided a discharge mitigation structure, such as a detention pond is what we chose to design. And this controls the drainage for the detention pond design and the discharge method.
So this is just a little bit showing on the specifications and standard that we use in order to meet project requirements. We use the COSA Stormwater Design Manual to find our rainfall intensity. We also follow the Coastal Code of Ordinances in order to be with compliance with the City of San Angelo. We use the FEMA flood zoning to perform research to see if our site was in an actual floodplain. And then some of the software we used to do the analysis was Civil 3D and as well as ArcGIS to find the topography of the site. So in this slide, we will be showing the existing conditions. The site was mostly grass and tree covered, and there's an existing caliche road as well as a parking area on the site. In the picture, we can actually see a white pickup that is parked on that road. There's housing that's adjacent to that site. The South Contra River is located on the south end of the site, downstream of the property, and there are 3 existing wellheads at this park. It's important that we preserve these wellheads as they serve water for the whole city of Cristobal. There's also a change in elevation of about 5 feet on this park, and with the lowest elevation being on the southwest end of the park.
For our analysis method, we had to consider this before actually performing the analysis of the site. It's commonly known engineering knowledge that if a site is less than 200 acres, you are able to use the rational method. Being that our site is just over 2 acres, we were able to use this method for our calculations. Along with the rational method, we are greeted with the equation of Q equals CIA, where C is a dimensionless runoff coefficient, I is the intensity of rainfall, and A is the area of each subbasin drainage sub-area. Our whole goal of doing a drainage analysis, like I previously stated, would be to get the Q peak, the maximum flow for the 100-year storm, to compare it to existing conditions. Over here we have an example of our calculations. I know it looks kind of scary right now, but this middle section here is mostly all constants given from the San Angelo Stormwater Design Manual. It all pretty much just boils down to C times the intensity times the area to get our flow. Based on the area of the site, we were also able to use the modified rational method for our detention basin design as well as detention basin calculations. And over here, we just have some tables from the City of San Angelo Stormwater Design Manual that we based some of our numbers off of.
So as through research, we found that, according to FEMA, that our site is located within a floodplain. So from this, it developed challenges that we considered. It allows us to, our goal was to mitigate flooding from the structures that are going to be implemented, as well as from the walking trail that is in place. We constructed a pre-development analysis. We first defined two different drainage basins, drainage areas. So one being the larger area and two being the smaller area. So we had the larger area being an area of 1.78 acres with a weighted C value of 0.33. We also did two studies of 2-year and one of 100-year storm analysis. The peak flow rate of the 2-year was 1.5 CFS, as well as the 100-year being 3.4. For drainage area 2, it was 0.19 acres with a weighted C value of 0.3, and the 2-year study being 0.4 CFS and the 100-year being 0.7 CFS.
So these are some of the grading considerations which we considered at the beginning of our project. Number one, we looked at doing a slight alteration of the existing grade. The second option was to grade the site to drain to a downstream shallow drainage ditch. Our third option was to just grade the site to a singular discharge point. All of these options have pros and cons. For our first option, it would be the cheapest solution, minimal cut and fill, and would require almost no grading or design work for the team. Our second option would be relatively cheap, but also use minimal cut and fill, and it would allow the team to design a drainage ditch for capstone purposes. For our third option, it would be a simplistic layout. To do this option, it would also provide a single discharge point, but we felt that this option would require expensive cut and fill. Ultimately, we decided to go with option number one.
For our post-development drainage results, you can see here, comparing the existing to the proposed, our C value did go up a little bit as expected, which made a little bit more flow from the site. You can see from the Q peak for the 100-year storm, we went from 3.4 CFS to 4.6, and we had to think of some way to mitigate this flow back to existing conditions. If you look at the image on the right, this is our drawing of our post-development drainage analysis. Just to kind of simplify this, in working in close correlations with the transportation team and designing that road through the middle of the property, we knew it was going to be extruding from existing ground a little bit, creating a natural open channel for the water to flow down. So essentially, this green line will specify our longest path of flow through the site. Starting in the northeast corner of the site, the water will flow through the parking lot, along the edge of the new road, and then, as we concluded with the transportation team, a concrete drainage flume would be the best way to get that water to cross the road. And you can see here, it crosses the road through the drainage flume and is routed through the detention basin and discharged to the existing culvert that is already under Loop 110. For our hydraulic structure, obviously we chose to do a detention basin. It was important for our team to comply with the standards set forth from the San Angelo Stormwater Design Manual. These included having an 8-foot top of berm for an earthen basin, 4-to-1 side slopes, 1 foot of freeboard from the top of the water elevation to the top of the basin, as well as the time to drain 100-year event would be less than 24 hours. As you can see in our design, our basin is developed with 4-to-1 side slopes, an 8-foot top of berm, 100-year water surface elevation of 1.50 feet, and a top of berm at 2.50 feet, giving us that foot of freeboard. Our detention basin discharge method, after a lot of trial and error, we decided to go with a series of 3 6-inch drainage pipes at various elevations. You can see here, this is kind of how they are going to be laid out for our discharge. And our discharge calculations here showed our 100-year discharge at 3.40 CFS, which is the exact same as it was existing conditions. You can see down here, drain time is 1.20 hours for the 100-year event, much less than 24 hours. And our storage provided is greater than or equal to storage required, which makes this a successful design. As from here, this is our final proposed layout design of the flow. The green line indicates where the water will flow through, and with arrows pointing in the direction of flow. Alongside the road, it would be an open channel from the proposed design of the road structure, and with the drainage flume at the end, and discharging into the detention basin that is there into the existing culvert. And from the outer area, on the outer side of the green, it is the offsite drainage that is flowing directly into the existing culvert that is on site. And now we will pass it on to the environmental team.
Okay, hello everyone. My name is Jonah, and this is my teammate Jet. We make up the environmental team, and we're excited to show you some of the things that we worked on for environmental this semester. Okay, for our first slide, Dr. Kitch, we were in foundations class last week, and we kind of asked him about our presentation. And we know you guys have been sitting here for a little while, and he gave us a note about presenting. He said, you want to hammer home just a couple of main points for your audience, because it's really hard to remember all these slides. So if the environmental team had one thing for y'all to take away about what we worked on, it's basically this. Miss Sylvia has a park. There are things that are going on inside this park, okay? We're trying to look at it from an environmental perspective. What structures are going on there? What are the living things on the site? What's living around the site? Are there bodies of water? Are there water, going to be transferred from the site off? We're trying to look at those things and determine, are there negative impacts to the environment that are going to be caused by these things? And if that's so, can we predict how or when that's going to happen, and can we prevent it? That's our goal. So through that perspective, I want you to remember that as we go through each of these 3 things or 4 things that we developed for our client and for this project. To get started, Jet and I and our team, we didn't have a lot of environmental experience. So what do you do when you don't have a lot of experience? You do research. There are specifications and standards for environmental. These are federal and state regulations through the Environmental Protection Agency, and local things, the TCEQ, that's a state thing. So these are the things that we use to sort of guide us when we weren't sure what to do. You can see a picture here on the right. This is the South Concho River. That's about 150 feet south of our site, and as you can see, it's beautiful. This water source is absolutely vital for the citizens of Cristobal. There's on-site wells that are on our site, and they feed from this water source. So this is one of our main things we want to take care of. I mean, as you can see, it's really pretty, and we want to take care of it so that people can continue to enjoy it, and it can stay the same as it's always been. That dam's been there for 150 years or something like that, so it's really interesting. To start, with environmental, we evaluated the existing site. These are all the things that are already there. You can see with the tree survey here on the picture on the right, Mr. Russell from SKG, thank you for doing that. Those are these white circles. These are very mature South Texas live oak trees, like Juan talked about for a second. 14 feet in diameter. That's like Jet and I holding hands and can't go all the way around them. Hundreds of years old, so we want to keep them that way. Trees make lots of oxygen. They're important to the environment. So we want to make sure as we go through these next couple of slides that they're protected, and we're going to talk about that. I spoke about the well locations. You see this laser? Okay. These are the well locations on site. There's one more site. From an environmental perspective, we just need to make sure that they're not contaminated. As you can see, there's chain link fence around them. That's very important, just so they don't get knocked over or some kind of contaminant finds their way in it and gets into the water table. We don't want that. Next, the bordering residents. If you look on the right here, to the south and to the east, there are people that live a rock's throw, very close to the site. For construction, we want to keep our noise down. We don't want to be offensive to the people around us. And then you'll see in the lighting plan, we don't want to have light pollution, which is any kind of offensive light shining in their windows, while they're in their house. So we're going to be thinking about the people around the site. I spoke to the South Concho River. It's very important. We're gonna make sure that, you know, nothing that's happening throughout our construction process is being transferred from our site off of it into the river. We just wanna keep everything that's on our site where it is. Our awesome hydrology team spoke about the topography. The southwest portion of this site is the lowest point. All the water and everything is gonna make its way down to this corner. So we're gonna put some BMPs that Jet's about to talk about in that area to make sure we're keeping that on. Concrete structures is more of a post-development thing with our band shell and our structures that are going on. We're gonna try to keep those in mind for, you know, how is it gonna change? How's the water runoff gonna change when we put those surfaces in place?
All right, so our team was able to provide the client with an environmental impact assessment report. This outline kind of shows how we wrote it. So we just scoped out potential environmental problems, and we came up with some different consideration of alternative solutions or best management practices. Some we thought necessary to kind of get in our report were sediment control fences, erosion control logs, backlight shielding, and noise reduction. Our report also confronted how these BMPs would affect things like geology and soils, traffic, floodplain, zoning, and overall safety. So our selection of BMPs was really just kind of based on engineering judgment. This is the decision matrix we provided our client of what we picked and why we picked it. These three were our main ones, so we thought the erosion control logs would be useful for runoff in the river. The silt fence would be useful for the material piles, and then just typical sanitary waste management is typical in any construction project.
Our next step after our our environmental impact assessment report was to provide the erosion control plan. To summarize what this document is, for those of you that don't know, this is the next step in the environmental process for the client to have all of their BMPs, or the client or the contractor really. They're gonna have a list of all of the things that we suggest, where to put these, and their application. For this erosion control plan, it's something that's important for a construction general permit. Robert and myself are gonna speak to that in the construction portion of this. One thing that I wanted to mention here for the vegetation preservation part, we found this document through the Environmental Protection Agency. It's a kind of a guide. You can measure a tree's diameter and convert it from inches to feet, and that shows you how close you can get to a tree with your construction without harming it. So you're thinking about the roots below the ground and the canopy above, because those trees are important to us. Our next step was the lighting plan. Ms. Sylvia informed us early on in the project that she had a set amount of solar-powered lights from Green Frog Systems. Once we found out that set amount, we began trying to do some manual calculations using this formula. And this process was just trying to visualize using the tree survey and these manual calculations where we could put these lights. For the manual calculations, all it is taking into account the height of the light, the lumens, and the beam spread degree amount, and just seeing, you know, directly what the light will shine on the ground. And that's gonna give you sort of an idea how they fit through the trees and how far you can put them apart. One important thing that we loved about these lights from the environmental perspective was this rotation angle that these lights have. We spoke about the residents around the site. It's really important that they're not seeing the lights from their houses or even driving by. So we utilize the rotation angle on the edges of the site to turn the beams, as we'll see in the next slide, in a way that, you know, it's not interrupting anything that's going around. So it's really awesome.
Yeah, so like Jonah said, we were able to meet with Green Frog Systems. We actually took our walking trail out there, and they were able to walk it with us to see where there was adequate lighting and where there wasn't. We also had a wheel to make sure we had efficient distance in between each light. And after doing this, we actually had to go and change our walking trail up a little bit, but that will be discussed later in the presentation.
Here's our final lighting placement. So once we had that meeting, the trail was locked in exactly where it should be. We went into AutoCAD, and using the tree survey and the trail locations, we marked places, these orange dots, with where the light should be. A couple of these lights, you see these yellow lines that are connected. Those are areas where there's too much shade and not adequate charging would be available. So we connected it with underground electric. It's a low voltage wire. So it won't need to be very, very, very deep, so it doesn't harm the roots. So those locations are good. Once we completed this drawing, I sent it back to Mr. Dave at Green Frog Systems, and he sent it to a photometrics engineer in Lubbock, Texas, and that's who came up with this image here you see on the right. If I could summarize what the photometrics process is it's taking the scaled measurements from our CAD drawing, and it shows basically what the lights would look like in the darkness. These small lines you see on the insert, that's kind of like a intensity of light from a specific measured distance from each pole. So it's really good to visualize what it'll look like in the darkness.
So just overall design constraints of our environmental assessment, which is from lack of previous experience and knowledge. So for our recommendation, we recommended the client to submit a notice of intent to kind of check our work and make sure we didn't miss anything big or get anybody in trouble for that.
And here's our final design. As mentioned, this is a low area to the southwest of the site. We implemented some erosion control logs in this natural low area and around this culvert. The hydrology team came up with their little analysis, their culvert underneath the walking trail, so there's a lot happening right there, so we decided to incorporate those. You see our lighting locations that we incorporated, the underground electric. On the south portion of the site, there is the silt fence and also around this playscape. There's people that live down here, so we wanted to put that border fence just to keep anything from running into their yard. I wouldn't want that. This silt fence right here around the playscape, as they're making that, this is a natural drainage area. So after walking the site, we just decided that might be a good thing to consider right on the corner of that foundation that's being made, just to keep it safe. To the north of the site, here is the place where the material is going to be placed. The silt fence will be placed around that just to keep it in one spot for the trail, when they're constructing that. And then also we have a silt fence to the top of the site. This is the highest point, and we just decided that it was the best idea to place that right there so that water could possibly be pushed east on this road and follow the ditch down. And now we're going to hand it over to the transportation team. Thank you.
Alright, so my name is Jet. We're the transportation team. Helping me out this semester was Nathan, Brian, and Juan. And I'll let Nathan tell you their scope.
So here are some of the tasks that the transportation team was assigned with. So we needed to make a quarter-mile walking trail, center access road, and a proposed parking lot. And for each of these designs, we're tasked with making a horizontal and vertical alignment, as well as cross-sections depicting the material used in the placement, and then an on-site layout.
So to get started on our transportation issues, we decided to do an on-site investigation to kind of see how the traffic flowed throughout the park. We found that this east-west road was really just kind of a cut across to avoid this intersection up here. This road going through the through the park was the access road for maintenance trucks when they perform maintenance on the wells. And this little cutoff road right here was just a private driveway to a residential house down here. So we didn't find it necessary to perform any pre-development and post-development traffic studies. However, in the report, we did include some pre-development numbers for Loop 110, as our parking lot could affect these numbers later.
We proposed our client with a couple of options that we thought of. Option one was the walking trail being a quarter mile that goes entirely around the park. It would be a permeable surface, being gravel or asphalt, and actually I got that mixed up. It would be of decomposed granite. The parking lot and the road itself would be of gravel or asphalt, and that would stay continuous for ease of access and ease of exit. Option two we presented was being a fifth of a mile that was on the southern region of the site, which is outside of the parking lot itself. And it would be an impermeable surface and the walking trail would be with either asphalt or synthetic rubber, which is the track material. This is the decision matrix that we use to conclude our material being used. For the road material, we considered with an impermeable surface and a gravel material. With the walking trail, it was, as per the client herself, she asked us to use a decomposed granite, and through this decision matrix, it was concluded that this would be an optimal use of considering the criteria we considered.
So these are some of the options we came up with regarding the access road. An important thing to note before we start discussing these options is this access road is only gonna be used by utility vehicles accessing the on-site water wells, and it'll be entirely closed off to the public. So for the first option, we left the existing access road that's running along the south border of the park, but we found out later that this is gonna interfere with future development. For the second option, our access road would dead into a roundabout, but again, this interfered with future development. And our third and final option had the access road dead ending in front of the existing stage that's on site, and we found this would be the perfect one. So this first figure just depicts the horizontal alignment of the access road. It's in red, and as you can see, it dead ends in front of this yellow square is the band shell where the existing stage lies. And it's gonna lay over an existing Caliche road, and there'll be no through traffic again, it's only gonna be used by utility vehicles. This bottom figure displays the vertical alignment for the road, that's gonna be in green, and this red slashed line, dotted line, whatever you wanna call it, is the existing grade. And this green arrow, it's gonna be pretty hard for some of you to see, it denotes the drainage flume that the hydro team was discussing earlier.
So for the walking trail, that's where our transportation team spent most of our time designing. It was an extremely high priority for the client, and construction has already kind of started on it. So we were under kind of a time crunch. This evolution of our walking trail is included in the final report. We ended up drawing about 7 walking trails. We encountered various issues such as property lines issues, and then we had some inconvenient extreme curves in our designs. We also presented the client with some different length options, just to kind of throw some more options out there. And right when we thought we had it figured out, we went on site to lay it out, and there was a few objects that were not in the tree survey, like some historical monuments that we thought we probably shouldn't tear down for anything. And then we also had to change it up for the lighting. I discussed earlier.
So as for our walking trail final design, it met all the length requirements of a 1/4 mile, which is great. And it stayed within the southern region of the site, which is outside of the parking lot, and it was offset from the center line 3 feet, and which created an efficient distance from the trees, and through the weaving pattern of our trail itself, it considered efficient sunlight for the solar lights that are going to be implemented. And with a decomposed granite finish, and we marked out the center line with stakes that we went out and placed ourselves.
So for the parking lot, our team decided to lay it on the east-west cut-across road. That way we wouldn't have to tear down any trees or kill any grass, we wouldn't have to. So this is our first design. Both we and the client agreed it was a little too close to this east side boundary, and we were getting a little close to a tree on the north side. So we decided to move it down a little bit. And so this design option 2, both we and the client were happy with. We used design standards of 9-foot wide spaces at 20 feet long with 1 handicap space. And there's a little area in between the parking spaces that one of our lights are going to be incorporated with.
So these are just some of the materials and quantities that we provided for our client. As the team mentioned earlier, the walking trail was our #1 priority, as they are going to be constructing it, or it's actually under construction as of right now, so woo for that. For the road, for the walking trail, we proposed milling out 6 inches of the trail, offsetting it 3 feet from center line. We provide cubic yards for both the base and the granite for that. As for the road, we also proposed milling out 6 inches, having a 10-foot width road, and doing 4 inches of base, an underseal binder, and 2 inches of overlay.
So using the materials Juan described, we were able to provide the client with some cross sections. Our client requested both a 6-foot wide walking trail at a 6-foot depth in the ground. So for the road, we didn't see a reason for widening it or narrowing it, so we just left it at the 10-foot width that we already had. And as Juan explained, we had the 4-inch flex base with a 2-inch overlay. And And now I'll hand it to Angel and the geotech.
So, thank you, Jet. As you said, my name is Angel, and I was the leader of the geotechnical team along with my partners Seth and Robert.
For the scope of the geotechnical project, we had to perform a geotechnical site investigation to determine how the soil was going to act under pressure of the loads that we are adding into the site. This was particularly difficult since we lacked a soil sample from the site, from farther down depths, I guess. We ended up having to go out and collect our own sample, being about a foot deep, and typically a geotechnical investigation like this goes much deeper, 5, 10, sometimes even 20 feet deep. This testing of this 1 foot depth soil gave us our soil properties and profiles. They do extrapolate quite a bit based on assumptions we had to make without the deeper soil sample. The foundations were designed for the family pavilion columns, the bandshell columns, as well as the bandshell walls, based on our geotechnical investigation and tests. And the structural design of steel reinforcement and thickness was based on the shear and the flexure of the structures that we were implementing. We had to work in really close correlation with the structural team to get these loads. For our specifications and standards, as I just said, we did have to work really close with the structural team. They found their loads based on the ASCE standards and the AISC standards. Like our biggest savior for this project was the foundation design book, and it does help a very large amount to have an author of this book be your professor as well, so I really recommend that.
It's a quick read.
All right, moving on, we're gonna look at the soil profiling and properties for this project. As we mentioned already, there wasn't any existing soil data, so we had to conduct our own soil analysis. We collected samples on site and did Atterberg limits and moisture content testing. Through this, we were able to determine the fineness of the soils and give us clues of the groundwater table. Another additional resource was the USDA. We were able to get this for the area we're inspecting. 2% of it is Angelo clay loam, where 97.8% is Rio Concho or dev soils being organic materials, unconsolidated. So going from there, with the online data as well as our own test results, we were able to characterize the soil as clayey silt, not silty clay. Very important. Those are two different things. Through this, we were able to get the unit weight, specific gravity, and friction angle, which helps us with our foundations, as I'll talk here in the next slide. For groundwater depth, we weren't able to find any hints of it near the surface of our site, so we estimated it to be 5 feet below the surface based on the river depth. Here's an illustration of some of the options we considered. We went with a shallow foundation design due to the lack of soil data, and because of the low loads from the structures, as we'll speak of later, there wasn't a need for deep foundations. The specifics of these are, for the bandshell and pavilion, we can see we use a square or rectangular footing size based on the moment loads, whereas the bandshell, we use a continuous footing as shown here because of the wall structure.
So to start off our foundation design, we start off with the geotechnical aspect of it. This would basically just determine how deep and wide our foundations would have to be. So our ultimate strength limits was limited by bearing capacity, and we calculated this using Tersagi's method. This would help determine the width of our footings. Pictured here on the furthest right just shows some failures that could occur due to bearing capacity. This is mostly just to make sure the foundation has enough space to distribute that load that it's going to handle, so the soil itself can hold it as well, and it doesn't uplift completely. Along with this, we also have to check serviceability limits to determine if the building will settle due to the soil itself. Usually, these two calculations run separately, and the highest of the two widths are determined to see which will control. However, due to the lack of knowledge of the soil and such, the width that was determined off the bearing capacity was inputted into our settlement calculations to determine if it was lower than the maximum limit. No max settlement specific numbers were given to us by our clients, so the group determined that the max total settlement should be around a quarter of an inch, with differential settlement around there as well. On to the second step of the foundations, we started with the structural parts. This determined our one-way and two-way shear. So as seen in the picture here below, too much loads can actually cause the foundation itself to fail. So we wanted to make sure this footing was thick enough to be able to sustain this, as well as to keep the column from simply puncturing through the foundation itself. Along with this, flexure was also done to determine the number and size of steel bars that will need to be inside this concrete, as it is going to be reinforced concrete, to allow this foundation to resist any flexure that may occur. Development length of the steel, as well as the spacing of the bars and thickness of the footing were done once more, as any changes of this should be double checked, as if more steel is needed, your thickness of your foundation is thicker, and you don't want your foundation to be sticking above ground. For our final designs, these are some of the ones that we came up with. Our bigger one here would be for our band shell, as since this band shell, as we will describe later, is at an angled slope, there's a lot of wind loads coming in. So we want to make sure this foundation is wide enough to handle this moment load, as well as to resist any uplift that may occur. Down here, we have the smaller ones for the band shell as well as the family pavilion. These don't have as many moment loads on it, so they can be smaller and not as thick. And since these will be connected with steel columns, they will be, the columns will be implemented to the foundations through steel plates and steel bolts. Here on the right, we have a picture of the continuous foundation for the walls of the bound shell. Unlike these, they're not gonna be square, they're gonna be long, continuous, as it is a wall. And due to the blocks themselves being masonry, they will not be connected through bolts, but rather through a dowel that will run through the center of the wall. With that, I'll hand it off to Nathan, which is our leader of our structural team.
Good afternoon, everyone. I'm Nathan, and these are my fellow teammates, Juan and Angel. I'm gonna go ahead and let Angel keep talking for a little bit.
So the scope of the structural was to design the band shell and the family pavilion of the area. The band shell will encompass existing stages in the areas. So for those that know, a band shell is simply a structure for whenever there's a band on stage or if there's a concert going on. The main focus of the band shell is to have its structure positioned in the way to where it will push the sound out into the crowd, so you're not having too much trouble hearing. They will also have to be made out of materials that require little to no maintenance. These structures, as well as this park itself, will be maintained over the people of Cristobal, so it will be mostly volunteer work. So these structures should not be too advanced to where you need special training or special equipment to maintain. Design of these structures included determining the loads that these structures would have to resist. These were done through LRFD combinations, which simply determine the combination of people that are going to be on there, any wind loads, any snow loads that are going to come in that the structures must resist. Once these are determined, the structural analysis part would come in to determine how these loads will affect our structure itself. Once this is determined, beam and columns will be selected to determine what is the best fit to hold these loads, as well as how these beams and columns will be connected. The specifications and standards that were taken by the group, the ASCE manual was used to mainly determine what loads to take into effect. So this would include dead, wind, and rain loads, determining based on the area. And these loads will be placed in our LRFD load combinations, as we stated earlier. The AISC steel construction manual was used for the structural steel design. This will help us determine what type of steel do we need, how thick does that have to be, how wide, as well as the connection designs for these members as well. Some of the construction materials the group decided to go through were steel, wood, and concrete. These were all decided through superior performance, aesthetics, sustainability, low maintenance. As we can see, you kind of see wood probably wouldn't be a very good maintenance requirement, especially if it's a lot of rain. You have to replace the wood a lot. So based off of these categories, the team decided that steel was the best way to go, as it has superior performance, aesthetic, it's sustainable, and it's very low maintenance. For the roofs of these buildings, the band shell decided to go with a single slope roof, as well as, again, the band shell's purpose is to push sound out, so any other roof would kind of defy that purpose. For the family pavilion, the group came between a triangular roof and a curved roof. The group decided the triangular roof would be the best design for it, as a curved roof would offer more room for error, as anything with curves requires more calculations, more loads, and it'd be a lot more difficult to calculate.
So for our recommended preliminary designs, our band shell is 40 by 40 foot in width and length, and this is just so it can encompass that existing 30 by 30 foot stage, that's on site, has a max height of 30 feet and a roof angle of 14 degrees. Our family pavilion is 20 by 25 foot with a max height of 15 feet and its angle is 26 degrees. So when running the structural analysis, we ran 2 different scenarios per structure. The difference between these 2 scenarios is just in the direction the wind was applied to the structures. So these 2 figures at the top just depict how the wind loads are gonna interact coming from different directions. And this is actually how we modeled it, Mastan2, which is the software we use to do the structural analysis. And this is the actual calculations we ran through in order to find the value for the load that's gonna be applied. So we jumped into the ASCE manual, found this figure. This figure will give us the design velocity for the wind in our area, which was 100 miles per hour. Then we calculated the velocity pressure, plugged that into our net design pressure, and the net design pressure is the actual value we needed. And a bunch of these other values are a bunch of constants found throughout the manual. So before we actually get to the structural analysis phase of our design, we have to run through load resistant factor design. And what this comprises of is jumping back into the ASCE manual and selecting the loads we're going to use. We selected a wind load, a snow load, and a dead load. The dead load consisting of the galvanized roofs and this is an initial weight of the beams, so we haven't selected our members yet, so we didn't know the exact weight. And then we plugged those loads into the load combination equations, which are going to give us our factored loads. What this does is it accounts for the uncertainty of the loads. And then we have our factored loads. As I was saying previously, we ran 2 different scenarios. For the first scenario, we have 267 pound per feet. For the second scenario, for the band shell, we actually had some uplift. That was when the wind was hitting the front of the structure, and that was from west to east. And for the family pavilion, it really didn't matter because it was geometrically the same on either side. So now we're on to the structural analysis phase. We ran a second order analysis, and what this means is the loads are applied in increments, and at every increment, the geometry is updated. And what this does is it gives us more accurate values for the internal forces throughout the structure.
So as Nathan and Angel mentioned, after running our structural analysis, we were able to obtain our ultimate moment, ultimate axial, and ultimate shear loads. From here, we were able to select adequate beams and columns for our structure. For our beams, we selected those based on ultimate moment loads, and then we checked for shear. For our columns, we selected those on ultimate axial compression. In the end, we came up with pretty small sections for our structures. We felt that these sections were adequate as we have very small loads. And we came up with HSS 4.5 by 4.5 and W8 and W10 sections. This is showing a 3D rendering of both of our structures, which we ran on Revit. We will have more detailed specifications on connections, beam placement, and the columns of the structures in the plans in the back room, which we encourage y'all to take a look at after this presentation.
Now we're gonna pass it on to the construction team.
All right, my name is Robert McLean. I'm the lead for the construction team, along with our environmental lead. Jonah was one of our members. So going over the scope of work, the primary thing that we did was a project Gantt chart. We had to coordinate with each team and figure out what tasks they needed to complete throughout the semester. Secondary, we did a construction timeline. This is to be used by the client for her subcontractors and those working on the project. Next, we went over required permits, as Jonah mentioned in the environmental section. We'll go over that later. We also created a demolition plan. There was existing concrete benches on the site that had to be demolished. Most of those are already gone. There is a demolition plan in the back of the room if you'd like to look at it. And then finally, to encompass the entire project, we created a project cost estimation. We worked really closely with all the teams. They did a great job of providing us with the data to get the project cost. So here's our project Gantt chart. I don't like the way this one looks, so we're gonna use a different one. So this is a program called Project Manager. We use this to organize all of our data for the project. As you can see, it is color coordinated. This color coordination also matches the Gantt chart, which is on the back table. We have it categorized by each subspecialty. hydrology, environmental, structural, geotechnical, and as you scroll down, you will see we have transportation, construction, and then the final report at the very bottom. We're gonna go over one of these aspects and one of the tasks. For an example, the parking lot design for transportation, we designated 9 days from 9/21 to 10-3. This program does not account for the weekends. It runs on a Monday through Friday scheduling, but I promise all of us did work on the weekends. Looking at who worked on this task, for our billable hours, we have Jet, our transportation lead, worked 3 hours. Juan, being a team member, worked 1. But you'll also notice Brian and Seth also worked an hour on this. That is because, as they've mentioned previously, the parking lot design and roadway layout did affect the drainage for the site, and so some of their hours were going to be billed towards this part of the project. You can see in the next column, we have a percent complete. It's 100% complete, as all the other tasks are, up to date. The column next to that is the priority, which can go from no priority, low, all the way to critical. And we'll discuss that whenever we go over to the construction portion as well. We designated 6 hours for planned hours, whereas the actual working hours was 7. And then the planned resource cost was estimated to be $535. That is a calculation of the number of hours worked multiplied times the rate per person. Each person has a separate rate based on their specialty and their position. So moving forward, this is our construction Gantt chart. So this is all of the stuff post-design. So you see we have this categorized as well. We have pre-con, site work and foundations, project structures, and beneath that is the project closeout. You can see some of these tasks were done by our team, such as the proposal meeting, site examination, and the walking trail layout. Those are all things that we conducted. All the rest of it is designated to a subcontractor, whoever is working the project. If you need any of this data from any of this, we do have it provided in PDF form, or you can email me. The free trial did run out yesterday. So as we did with transportation, we're going to look at one of the tasks for the subcontractor to give you an idea of that. We're gonna go ahead and look at the very first task they have under project structures, which is the band show. This is designated for 10 days worth of work from January 2nd to January 13th. Again, keeping in mind, this does not calculate the weekends. It works off of Monday through Friday scheduling. So off of those 10 days, we estimated that it would take 100 working hours. This is off of a 10-day working schedule. So 100 hours worth of work is considered. This is a critical priority as it's one of the main structures for our project. As we continue to scroll, you can see plan cost, $69,000. That is the cost of materials. So that is concrete, rebar, steel, anything having to do with materials. Whereas planned resource cost, that $19,500, that is, again, the hourly rate of the subcontractor and their workers multiplied times the number of hours that they worked. You can see that the actual cost and planned cost are identical because they are materials, and then the planned resource cost will be estimated once the contractor finishes and their hours can be calculated. I'm gonna hand it over to Jonah to go ahead and talk about our permits for the project.
The main thing that we want you to take away from the permitting and the research that we did for the permits that are needed is that Cristobal is an unincorporated community. They don't have a Department of Transportation or any kind of things like that. So the things that we included and did research on are federal and state standard specifications, similar to what we did in environmental, and these are the things that this project should be held against in order to proceed correctly.
Yes, as Jonah mentioned, so some of these permits, as you can see, the building, demolition, and contractor registration, that all needs to be filed through the city, through their board and their commissioner. Whereas electrical, water, air, those are national standards that need to be followed, that require inspection. Same with environmental and concrete, you can see they require on-site inspection with SW3P and ACI through a certified inspector, which I am, so if you need one. Yeah. Here's our project cost estimation. We have it color-coded to match all of the items you can see in that top right corner. We're gonna just zoom in on a small section so you can see clearly what we're illustrating. We adopted the item number and code numbers that TxDOT uses for their filing systems because we use their average low bid pricing, which gives us the best estimate of the cost of materials up to date, as well as the cost of labor. In conjunction with these numbers correlate to the TxDOT specifications manual to give us an idea to make sure we're using the correct item number for each of these. So some of the things illustrated here you can see are erosion control measures. As we mentioned earlier, the erosion control logs and silt fence. One thing you'll notice is the prefabricated playscape. TxDOT doesn't build playgrounds every day, so this is not in their manual. So this is a special provision item that we have put in place here. And with all of these numbers, we can go ahead and look at the project manager desktop dashboard. And this gives us kind of an oversight of the entire project. As you can see, tasks, we've completed 39 of with 17 remaining to be done by the subcontractor. You can see all of our progress bars for each subspecialty. Another interesting thing, as you can see in the bottom right, is the workload per member. You can see how much we've done and all of our completion. Anthony, Dr. Battistini, you're kind of lacking on your tasks, so that's okay. But to encompass the whole project, you can see in the bottom center, we have our actual cost of the project. And what we estimated with all of our teams together is a projected $829,000 for the project. Of this, $287,000 is the resource cost. Again, that is the cost of labor and their hours, with $540,000 designated to task, which is the materials for the project. So that's the end of the construction presentation, and I will pass it along to our team lead, Juan Vasquez.
So lastly, on behalf of the whole team, we'd just like to once again thank our client, Ms. Sylvia Pate, as well as the board of directors of Cristobal City Park. We'd like to thank XKG Engineering for providing the survey for the park. We'd also like to thank the professors here at ASU, as well as Texas Department of Transportation. Just some of the key takeaways that we felt we improved on during this project were we got to use our technical skills, which we have learned throughout our 4 years here at ASU. We also improved in communication, both with our client and just with ourselves, and just working as a team. And we felt that these skills are skills that we will take with us throughout the rest of our careers. At this time, this concludes our presentation. Thank y'all so much.
I have a question.
Yes.
So you were all the biggest group of the day. You can really tell that you worked well together, so I commend you on that. My question is, how did you determine who was the lead for each section of your project?
So at the beginning of the project, we had a vote on what subdisciplines everybody liked.
Interests,
And
basically.
yeah, basically what was everybody's interest, and we decided to kind of put everybody where they were most comfortable, just to, make the project a little bit better for everyone.
One really good thing about our team was we had a couple of people step up and do some things that they didn't necessarily want to do. So everybody was very positive, and so
Yeah.
not everyone got to do their number one pick, but the people that got their second or third did a really good job in their section. So it really came together really good.
I'm curious about the decomposed granite instead of like asphalt or cement.
Okay.
What is the maintenance and expected life of that surface?
Yeah.
I'm not sure on the actual maintenance on that, but what I will say is that the reason we opted to go with that is just because that's just something that our client preferred, and we did propose like a concrete walking trail, just because it would be lower maintenance, as well as, I want to say at the beginning of our project, we proposed like a rubber type of walking trail. But really it was just preference and just look on that, so.
And one of the parts of Capstone is like the socio-economic impacts, right? It's like what's your design gonna have its impact on everything that's going around. And it's like we spoke, Cristobal's unincorporated, so Miss Sylvia and Joseph are literally volunteering to come and meet us there. They're not getting paid by the hour to come and do that. So any fix that needs to be happening from the trail, if it's asphalt, then were they gonna get a sledgehammer and come out there and break it up? No, it's easier for them to have that crushed granite and then just pack it down.
The other consideration for crushed granite for us is that we have water lines running throughout the park because it is the center for the water system for Cristobal. And so we had to be able to have easy access to any of the lines should they rupture.
I noticed some dark spots in your photometrics. Once you got those photometrics back, did you notice that? Are you gonna address that?
Yes, sir. Based on, are you referring to the middle of the site or between the lights, the gaps?
It seemed like on the walking trail, there was a couple of dark spots. There was one spot in
the
particular
south
that
side.
didn't have.
One of the major restrictions is the trees and the hardness of the ground as well as the roots. We're very restricted with overhanging canopies. So the spacing that we did, Nathan was on the wheel and we went, as far as we could, and then we look at the trees and it's like, well, we can't put it here, we're gonna have to go a little bit farther. And so you kind of look up above, and based on not trying to cut, trim any trees, that was the best that we could do. And that's what the photometric guy provided us, so that was the cost of that.
Your playscape was very close to your detention basin, plus it seemed like maybe your invert for your drainage appeared to lead right through that playscape area. Was there any thought about the dual purpose water park and playscape, or was that, any thought put into that?
Cristobal kids, they play in the mud anyway. So.
We are looking for corporate sponsors for additional amenities.
So down there, yeah.
So we weren't planning on super high velocities to meet erosive conditions, which won't really affect the playscape. And as we kind of talked with Jonah, he did implement one of the silt fences right along there just to help mitigate the flow and route it through the basin without affecting that of the playscape.
It could be a pretty cool slip and slide though.
It could be. If we needed it to be, it could be.
So related to that, you talked about BMPs, but those are mostly construction BMPs. Did you guys look at discharge standards and did you deal with NEPDES discharge standards?
So based on our
you talked about how important the river is, but
Yes, sir.
all the controls I heard were during construction controls.
Yes, sir. So based on the research that we did through the standards, through TxDOT, the Environmental Protection Agency, like we said, we're trying to consider what's happening on the site. These structures are being built, sediments being broken, there's gonna be loose soil, so those are the choices that we picked.
That's all construction stuff.
Yes,
My
sir.
question is about the long-term
The-
discharge standards. So
post-
water quality, you guys took care of the quantity thing,
Yes, sir.
fine, but I'm talking about water quality and the discharge.
So in our erosion control plan, there are certain measures that we considered. We didn't include them in our presentation that weren't applicable to necessarily soil and things like that. There is a water quality analysis that we got from the EPA on the water that is currently in, or not currently, it was about 10 years old, and that was the most recent data that we could obtain from what is going on with that water source as far as quality. That was the only thing that I could find.
Based on your question about discharge velocity, we complied with the San Angelo Stormwater Design Manual, and if the velocity is greater than 60 per second, we have to have the energy dissipation measures taken. Our energy was 5.7 feet per second, so it was under that 6 foot, so we didn't need to put anything for energy dissipation.
Speaking of that, I noticed you chose to use a lot of San Angelo standards. You want to just quickly talk about why you chose those standards and whether they're appropriate?
Well, Cristobal.
Yeah, so
Well, I know, I didn't say it was a hard question.
Being in the county, they don't have to enforce detention basins and stuff like that on county projects. But being as it was so close to San Angelo, we did like to use their standards for all of our sections of the project.
Yeah, we felt it would be appropriate, so, just like Seth was saying, being that it's really close to San Angelo, so.
Yes, sir.
Yes, sir, Lance.
All right, so I've got a question. Is it in the floodway or the floodplain?
Floodplain. According to Mr. Bill Ford and the research that we did, it's a zone AE floodplain, right, Seth?
It was both a floodplain and a floodway.
Okay.
What's the difference?
Trying to remember the difference.
Building
We
building
read about
requirements.
So the only reason I ask is because the floodway has a 0 rise requirement, which means you can't put a structure in the floodway
Mhm.
without a clomer and without a no-rise study, as well as coordination with FEMA.
Yes, sir.
And from the map, it looks like the site's pretty much cut in half, so that way the entire playset area and the detention pond and the discharge is always, is actually in the floodway, not in the floodplain. So did you guys have any direction, or get any directions in addressing that differently?
Yeah, so right now, I think that's something we kind of just may have overlooked, but something that we could definitely implement in the future moving forward.
From our discussions with the architectural firm out of Austin that we've used also on this project, they indicated that unless we had structures that people were going to inhabit, that the floodway restrictions were not as important.
Technically, it only affects the insurance requirements, not the construction requirements. If you're in the floodway, it is a no construction unless you can prove no rise,
So would that apply to the playscape?
anything.
Dr. Peña? Yes, sir.
Yeah, a question for the hydrology team. I noticed, it seemed like the outlet of the pond had three barrels or 3 pipes, but they were not at the same elevation. Well, why do you choose that design? How do they work when there's a storm coming?
So in the event of a 2-year storm, obviously it would go through the lower barrel. We had it originally designed for a singular barrel discharge, but like our optimal size was 10.5 inches of PVC, like a 10.5 inch diameter. And to my knowledge, they don't sell a 10.5 inch diameter PVC. So we elected to do like the structure that we chose. So essentially, at a lower storm, with not as much intensity, not as much rainfall, it would go through that bottom barrel. Whereas the higher the water gets, the more discharge that's conveyed through those pipes. That's actually a pretty common discharge method, similar to what we have in our detention basin on ASU.
For the band show, y'all don't plan on decorating with textile road signs like Cooper's, are y'all?
So right now, no.
We didn't include those in the drawing.
You're asking the wrong person.
Well, we'll-
Y'all had mentioned in your, in the geotech side that y'all went out and actually did some site exploration to find out, I guess, the different layers of soil you had. Was there any further research done, being that there's a bridge, pretty much adjacent to the site, was there any research done on, being able to extrapolate the strata that was found in the geotech exploration on the bridge?
So we try to, we try to look for a soil profile in that area, and we couldn't really find anything, and I actually spoke to Nick, and he said that, that bridge is so old that we probably wouldn't even have the, soil profile.
I think those bridges, like the other ones on Duck Creek and all, were done by the Army Corps of Engineers back during the, time, because we had one on our property that was done by the Army Corps, and they're very interesting, but, yeah.
Is that just for the bridge right by there, or is the one that's the freeways on, the highway's on right now? Is that one the highway's on right now, it's not that old, right?
I actually asked the colleague Drew himself, asked him if he could ask around, and he asked about these bridges, and he said that a lot of them were, they didn't have plans for, and the ones that they did have, a lot of them were just the plain gravel that they used after when they were constructing it, so it didn't really show anything that was any deeper.
They were during the time of putting people back to work and all that stuff. They're really, yeah, I've studied several of them really closely. They're interesting. So, yeah.
Not the one that's on the highway right now, that's a different bridge. Where's that question? Thank you.
As a previous teacher, I often see students work so hard on projects that they're doing, but for you guys to be able to, for it to be in construction That is so amazing. So congratulations to you guys.
Thank you.
One of you belongs to me.
Thank you,
And
Mom.
so- The amount of work that is put in, I know that you guys have too, because y'all met here and at home. So congratulations, guys.
Thank you.
What do you use
Great
for the
job.
billing rates? That's what I wanna know. Seriously, what were the billing rates that you used for your own team?
Oh. It depends on if we went out there on the weekend or during the day.
So I tried using the P&L sheet that we did in professional practice, and no matter how much I messed with the numbers, we were always at a loss in terms of like profit and loss. So I scrapped that. What I used for our team was the average cost per subspecialty. So the average salary of like a hydro member, geotechnical member.
Yeah, well, where'd you get those numbers and what were they just approximately?
Yeah, what do you use?
For majority of us, it was $35 an hour, and then Juan being the project manager, the head honcho, he got 45. And we couldn't afford Dr. Batts, so he had a raise.
Right, that's your base salary.
Kyle, you got a question?
Yeah.
Yeah, you mentioned you have one handicapped parking spot. Based on the available parking space, how does that meet with ProAg standards?
That's the standard.
We just, some standards that we looked at, it said that there was only one required for like, I think it was less than like 20 or something like that. And, we really only had like 10 or 9 spaces total, so we didn't think it would be necessary to add, any more than one.
Those are pretty low billing rates.
That's really low. Are you all getting your licenses for your engineering licenses, taking your fundamental exams and gonna get your, very good. Civils do that more active, and civils do it more than us mechanicals, it's important. Take your fundamentals exam, get moving.
To answer your question further, that was our rate as if we were working for a client or working for a firm, and then that was multiplied by, I think, 2.3 to get the rate.
So you did
for
use
the
a
firm.
multiplier on that?
Yes.
Okay, cool.
So we used 2.3 to multiply, so really it's more like $60 and $80 per.
Okay. Good.
And another good way to do it, we typically do it as well, is percentage of the project, is you're charging your fees as well.
I forgot we had to.
You forgot your consulting fee.
Related to parking, there's a band shell there, so I'm assuming when they got bands that you're gonna need more than 8 parking spaces. Did you discuss with the client, you know, how they, I mean, that seems like a perfectly appropriate parking lot size for, you know, the general use of the park, but did you discuss transportation and parking issues when there is a large function there?
We did, whenever they have like big cookouts and stuff, they said, they typically park to the side of the Loop 110, and, that's
Just-
typically how they.
Just like West Texas, they pull off the side of the road, just park.
That's what we do.
Sorry, one more.
Any questions? Yeah.
One more, I'll stop. With the inclusion of the handicap parking space, was any research done on if crushed granite was actually an acceptable, like, ADA material? Or
No,
like-
for the parking lot, well, the crushed granite was only for the walking trail, actually. So our other materials, what were used for the parking lot and the road, so we plan on those two being the same material. So just typical asphalt.
So if like somebody in a wheelchair wanted to like go to the playscape, is there an actual ADA path to it?
We'll have the road going down the center of the park, which that'll be pavement, so. But as far as like.
By ADA standards, I'm not sure you're required to supply a path for the wheelchair all the way down in a park.
Yes, you do.
You do?
Yes.
Really?
All elements have to be handicap accessible.
That's interesting, because every single part of this now has to be handicap accessible by ADA?
Whatever is considered an accessible element, a playscape where other people can go, or something that a normal person would use, other than maybe the walking trail.
I'm just curious, because I was handicapped for a long time, using handicap, so I'm very curious now as to what we require people to do that. What we require to be able to handicap access.
Bench shell and the playscape probably.
They would be, okay, so interesting. That's gonna add a lot of cost.
trail will have a ramp up the back and place steps that will have access just around level.
But actually a path to them, that you can access, would it be asphalt with a wheelchair?
It will be the crushed granite walking trail.
I got a question.
Okay.
How different were the like codes you had to deal with being in an unincorporated area versus San Angelo?
As far as like standards that we use, because this was in Cristobal and not here, well, we use the City of San Angelo, like for the hydro stuff, we use the COSA standards, just because since this is like outside of San Angelo, it's kind of like the closest thing that we could get. So
were there permits through the county?
Yeah, some of the construction permits, like a building and demolition permit, those are done with sign off through a subcontractor and through the city of Cristobal and the board. So those are how those are signed off.
So a lot of the work wouldn't be inspected in a way that it would in a city area.
Correct. Just the environmental aspect, stuff that's under national standards.
Okay.
Any other questions for the team?
What was the biggest thing you learned? All the way through. Number one thing you learned in the whole project?
I think the number one thing I learned is everything affects everything. So I know we went through the walking trail design, like, I don't know how many times, but everything affects everything is
Yeah,
probably
and I'll add to that, we've done projects in 2 and 3 people before, but we've never done like groups, okay? And for groups work on the same project for an extended amount of period. So like he's saying, the transportation team works really hard all week on the trail. We show up on Friday, the environmental team works really hard on the lighting plan. We meet up, the lights in the center of the trail. You know, and then the structures and the geotechnical team speaking about, oh, we made this design, oh, well, our foundation doesn't hold that design. So it's that communication and that teamwork to stay even with each other and communicate, and that way we're not taking a step forward and 2 back and 1 step forward and 2 back. Right, probably.
I think for me, it was the communication between the subspecialties. No aspect of this project was independent of the other, as we've stated earlier. If you edit the walking trail or you edit any of the structures, that affects the foundations, that affects our drainage analysis and where we expect the drainage to go. So just working with each team member, we met every single week, every Friday, and even days outside of Friday to discuss work on the project and make sure that none of our elements interfered with the work of another team.
Mine was communication on a little bit different aspect, to where when you open the drawing that everyone's working at the same time, you know what to expect. You don't open it and there's like 750 new things, and you're like, well, how did these get here? Are these right? You know, like, what do these mean? Everyone was able to communicate, like, hey, I'm gonna be in the drawing at this time, and I'll let you know when it's back uploaded so you can download it and work on your stuff.
For me, I guess I would piggyback a little bit off the teamwork, but it's moving as a group. So as Jonah said earlier, a lot of different teams have to work together. For instance, the geotechnical and the structural, and a lot of it is just working together. I mean, geotech can't do much; they don't have their loads from the structure team. So it's just moving at a pace to where everyone moves along and no one gets left behind. You don't want to advance too far, and next thing you know, well, the market control hasn't even been done yet. So it's just moving as a group. So having that communication and that teamwork between each other to make sure you're holding each other accountable and pushing each other to keep going as well.
For me, it was mainly communication through each individual team themselves, how one part affects the other. So like the walking trail, we couldn't really do hydrology unless the walking trail was finalized or the road material was in place. And so, yeah, that's pretty much it, just communication within the teams themselves and allowing the project to move forward smoothly.
I'd probably agree with everything that they said, because I was in charge of the walking trail, and every time I changed something, somebody would get upset. even though they told me to do it, but yeah, just communication, it was very interesting to have that many people working on something.
For me, it would be teamwork, you know, working with each one of these guys has been great. Everybody on this team is great. And it would also be client communication. We found ourselves communicating with our client on a regular basis, and so Coach that was really important.
And I'll add to that, Miss Sylvia, I know you feel like every time we go on the site, you were like, sorry, I'm thinking about changing this, but it was our goal, you know, to give you what you want, right? Because you're only gonna do this one time. And so Cristobal's beautiful, and it's gonna be a lasting change, you know, so as many changes as we did with all of our designs, we wanna make sure that we get you what you want, so.
Well, and y'all were flexible and just the ongoing contact was fantastic, so thank you all so much for all your work.
We couldn't have done it without the hammers you gave us for the stakes. We showed it for the stakes, but not the hammers. So, for the trail, so for sure.
Did you have a question, Dave?
Yes, for the parking lot being uphill, the park itself, do you guys consider putting in any barriers for any potential runaway vehicles, like wheel stops or any type of physical barrier or something?
We have wheel stops in the cost estimate.
And I think that roadway is like 30 miles per hour max speed, so we're only thinking anything too crazy like that.
How much, if you build, Cristobal, based on your, building rate, if you build Cristobal, how much money did they save by the free labor? Yours.
Oh, gosh,
You had that in there, right? I didn't see that.
yeah, pretty much that labor cost about 200K, I guess.
Okay, just wanted to know. $250,000, huh?
That feels great.
Sure.
You sound like a consultant. He said 200, you said 225.
Before we end, I do want to say one thing about our team. It was evident, you know, from the first day, we're all very positive, and you know, we were all directing the same way. We want to get this done, you know, no matter what. But our team leader did a great job by, you know, spurring positivity, right? He never asked anybody to do anything that he wouldn't first do himself. It was more of like, I'm gonna go do it. We're like, no, stop, do not. You know, all of us, you know, everybody, most people have jobs, you know, and we would meet during the week. Everybody would get off of work and we'd come to the schools, and we had this running joke. You know, we asked each other, how are you doing today? Well, we're in the trenches, but we're there together, right? Because we don't quit. And so it was really fun. And it was nice to have that positivity, you know, to kind of back it. Because subconsciously it's a daunting task. And so it was really awesome. So thank you, Juan. Really, thank you all.
Good job.
All right, if there's any other questions? Ms. Sylvia, I think you wanted this, did y'all want to say one last thing?
I feel like the only thing I can do is keep repeating how wonderful they were. Joseph is the vice president of our nonprofit, and I said I'll probably cry, so I can't say the ending remarks, but I think I'm good now because y'all ask so many hard questions. I have been slapped into reality. So we are a nonprofit, you know, Cristobal isn't incorporated, so every little improvement we can make, we're doing it by begging and pleading and asking SKG just to not charge us for the survey. And so we appreciate your patience, all of you guys, and thank you again. You will have a lasting memorial put into the Legacy Trail with your group name on it.
Thank you.
Thank you.
Great job.
Thanks for tuning in.